Okay, good morning, everyone. So maybe I can begin the introductions for this particular session. So good morning, and we're now in our second week of the celebration of the 40th PAASE anniversary in 2020 APAMS, or Annual Scientific Meeting here in the Philippines. So this is the first time that we're holding our sessions online, and the conference will be available until August 14. So we have different sessions every day from Mondays to Fridays. So later I will share with you how you can get access to the full program of our session. So I am Kathleen Aviso, and I will be chairing the session today. Together with me is Dr. Angeline Lau, who is from the Mathematics and Statistics Department of De La Salle University, Manila, who will be co-chairing this session. So this session is dedicated to topics on the different dimensions of COVID-19. So I'll pass it on to Angie so that she can introduce our first speaker.
Morning to all of you. Our first speaker is Professor Robert Schmidt with a question mark. Okay, so the question mark is really part of his name. So he's the professor of disease modeling at the University of Ottawa. I met Robert in an annual meeting of Society for Mathematical Biology. And since then, he has been visiting us here in the Philippines, collaborating with Filipino researchers and mentoring Filipino students. So using mathematics, he studies infectious diseases such as HIV, malaria, human papillomavirus, COVID-19, and neglected topical diseases and zombies. Okay, take note, you didn't hear me wrong, it's zombies. He has published 19 books on academic and pop culture, is the author for over 100 academic publications, is a winner of Guinness World Record for his work on modeling zombie invasion. Okay, so was the winner also of the 2015 Mathematics Ambassador Award given by Canada Partners in Research Association. And he also won the 2018 Society for Mathematical Biology Distinguished Service Award for exceptional contribution to the field of mathematical biology and its advanced research outside academics. So without further ado, let's all give a virtual clap to Professor Robert Schmidt.
Great, thank you very much for having me. I'm delighted to be here. Sadly, I can't be in the Philippines, but I guess the time difference for me means it's 8 in the evening rather than 8 in the morning. So I guess there's some advantages. Okay, so I will just share my screen. I'm teaching a summer course right now, so I've become an old hand at doing Zoom teaching. Let me just back up a little. Sorry, that was from my test. There are many kinks that need to be ironed out with Zoom teaching, of course. Okay, so I'm going to talk to you about this little known disease called COVID-19. It's quite amusing to me as a disease researcher of 20 years to be suddenly dealing with a global pandemic. I've dealt with smaller pandemics in my time, so this is quite fascinating. And in particular, I'm going to talk about COVID-19 on a university campus and discuss some issues of physical distancing. So I'll give some background about the disease. I suspect many of you know many things about it, but perhaps not everything that's relevant. Talk about the study that was requested. It was requested on March 12th, so we're kind of looking at a snapshot in time. I'll introduce the mathematical model and discuss various potential scenarios based on known data, talk about some decisions that were made as a result and further developments that have come out. So, as you may know, COVID-19 is a respiratory disease with flu-like symptoms. It's the causative agent of a potentially fatal disease that has significant public health concerns, as we all know, I think. It originated in Wuhan, China in late 2019 and has since spread quite significantly. I think that the spread is what is really notable for this disease. Common symptoms include fever, cough, and fatigue, but other symptoms include sputum production, headache, hemoptysis, diarrhea, dyspnea, lymphopenia. So some are more common than others. And I mean, this is not a fun disease to catch, but it can be quite mild or it can be quite severe depending. The period of onset from symptoms to death ranges from 6 to 41 days. the median is 14 days, but that's age dependent. It also depends on immune status. If we think about younger people, and because I'm going to consider a university campus, I particularly do want to think about younger people for the most part, that median is about 20 days. So it's a little bit longer. But I will stress that all this data, and particularly what we knew on March 12th, which is the date that I'm most concerned with, this data is preliminary. And so some has been revised since. Some things we know, some things we guess, and some things we have no idea about. However, that's always the case with diseases, right? I think there's more focus on this one because it's so global, that we're always kind of making best guesses, sometimes making very accurate statements about what we know, but sometimes there's large ranges, as you can see here. So some of the timeline, on January 22nd, there were 425 laboratory confirmed cases in Wuhan. The initially estimated R0, the reproduction number for the disease, that basically tells you the number of secondary infections, that was estimated at 2.2. That's since been revised. The doubling time was estimated at 7.4 days. By February 16th, it had risen to 51,000 cases. By March 3rd, it was 90,000 cases. On March 11th, it was more than 118 cases. So you can see the very rapid rise in the number of cases here. And March 11th is important because that was the day that it was declared a pandemic by the World Health Organization. Right? So suddenly this disease was a honest to goodness pandemic, and that prompted a lot of questions about what we were going to do about this. So on March 12th, the University of Ottawa in Canada, where I'm at, they requested an informal modeling study to answer the following questions. What combinations of transmission rates and serial intervals make for the best case, and what make for the worst case? And what's the consequence for outbreak size and potential mortality on campus if we wait until case 1 physically appears on campus versus being proactive? Now, this makes it look a bit more formal than it was. What I actually got was a panicked email from the upper administration, and they said, we have no information, right? No one has done these studies. We need it urgently, help. And so they asked a couple of colleagues, but other people were traveling that day, which, you know, was a quaint thing we used to do. And so basically I was the only one available, and I had very little time to do this. This was all done in a single day. Actually, it was done in more an afternoon and an evening because they needed answers quickly. All right, so we developed a model, and the model consists of 6 compartments. There are susceptible individuals, so those who do not have the disease, but are potentially able to catch it. There are exposed individuals who are infected, but are not yet symptomatic, and also, more importantly, are not yet able to transmit. Right? I care way more about the transmission ability than I do about the symptoms. Of course, an individual cares about their own symptoms, but as far as disease modeling is concerned, we care about, can you transmit? So I'm going to define symptomatic individuals as those who can actually transmit. Right? There are also asymptomatic individuals who can also transmit. As I said, I don't care that much about the difference between symptomatic and asymptomatic, but what I do care about is their relative transmissibility. So how much more or less efficient is a symptomatic individual versus an asymptomatic individual at transmitting the disease. There are recovered individuals who have had the disease and then since recovered, presumably with at least some immunity. And then we're also going to consider the dead individuals because we'd like to keep track of the case counts. All right, so yeah, I'm defining symptomatic individuals as those who both have symptoms and also are capable of transmitting the virus. Asymptomatic individuals do not have symptoms, but far more importantly, they can transmit, but they transmit at a lower rate. Right? These individuals may also recover faster, right? So because their immune system is not as overwhelmed, they may have less bad time of it. Exposed individuals are infected, but not yet infectious. And death here is only due to the disease. So I'm thinking about a short timescale and particularly a sort of campus population of much younger people who don't tend to drop dead. So the death here, we're only thinking about disease-specific death. Also, we're not replacing susceptibles. So it's a fixed population effectively. And certainly we're not talking about new students arriving anytime soon. New students tend to arrive in, say, September on campus, but that, A, is probably not going to happen this year and also wasn't happening in early March. So here's our model. Let me define all the terms. We have susceptible individuals, we have the exposed, we have the infected who are symptomatic and also asymptomatic. We have dead individuals, we have recovered individuals. So beta here is the baseline transmission rate. That's the transmission when a susceptible and an infected symptomatic individual meet. So basically, what's the chance they transmit? Well, what's the chance that they meet in the first place? What's the chance that transmission actually occurs, and so on? That transmission is modified for asymptomatic individuals, so it's presumably less, although in theory it could be larger. And so they have usually a less transmissible case. some fraction of exposed individuals will be asymptomatic. So fraction P moves into the asymptomatic class and 1 minus P remains in the symptomatic class. Kappa here, well, I've kind of called it the rate of developing symptoms. More formally, it's the rate of leaving the exposed class. So they either develop symptoms into the symptomatic class or they move to the asymptomatic class. There's a leaving rate from the infected class, and they can leave either due to death or due to recovery. So F is the fraction of individuals who recover. There's also a amplification of recovery for asymptomatic individuals, right? So they may recover much faster because they didn't get as infected. So their viral load may be lower. All right, so there's my snapshot of my mathematical model. So let me write down the differential equations, which is basically exactly the same thing, right? So I have my 6-compartment model, and you'll notice here there is no entry into the S compartment. So when you're in S, all you can do is be infected either by symptomatic or asymptomatic individuals, right? And then you move to the exposed class. Just bring up the mouse. So you move from the symptomatic, so the susceptible class to the exposed class, and then you leave the exposed class where you can go into the symptomatic or asymptomatic class. You leave the symptomatic class and you recover or die. You leave the asymptomatic class and we assume you just recover in that case. Okay, so there's my model. And let's think about what we knew, right? So on March 12th, we had some information that we knew pretty well, but not everything, right? So we knew that 17% of the population was asymptomatic, that the low risk death rate, so particularly the death rate for individuals under 70 years old, which we can assume is very good for a campus, that was 0.2%. So most individuals on campus are low risk. Now, not everyone is. Of course, you have some older people like professors, although even then, those age ranges are spread fairly widely. So I think it's fairly safe to assume that most individuals on campus are fairly healthy in the scheme of things, although they don't have to be because this is an average. The incubation rate was 3 days, although the range was quite large there. And it takes 20 days, as we said earlier, from the onset of symptoms to death. That reproduction number by this point had been updated to 2.35. And there are 42,000 people. Well, that's the total population, if you will, of the University of Ottawa. Now, not everyone is on campus at any given time, and other people come in and come out. So there's significant heterogeneity here. So caveats, this was very early stages of a fast moving epidemic. So the data that we had was the best that we had. And this data is, obviously going to get updated shortly afterwards, or the data may not exist at the time and then is discovered later. So this is basically a best case scenario with what we had at the time, right? Yes, and as I said, not all individuals would be on campus at any given moment. So N is probably an overestimate. And there's significant heterogeneity in the susceptible population. You have a large group of people who are young and presumably healthy, although not necessarily all. And then you have a smaller group of people, so professors and service staff and so on, who are older and presumably not quite as healthy. So like that's all possible, but we didn't really consider that. We just basically said it's effectively a young and healthy population. All right, so for the model, we can analyze this there is a disease-free equilibrium, right? That's given by everybody being susceptible and nobody infected or dead. So N here is the total population on campus. And initial conditions to be considered were everybody susceptible and one symptomatic individual. All right, so we assume one symptomatic individual arrives on campus. That's basically mirroring the question that was asked, saying what happens when the first positive case appears. Right? And I should say it's rare for me as a disease modeler to kind of be able to play with these kind of initial conditions, because usually your disease is endemic in the population and you're sort of worrying about how to get rid of it rather than waiting for it to arrive. So this was in some ways very exciting, at the same time quite nerve-wracking. All right, so to analyze this, we used the next generation method to find R naught. So we found our F and V matrices. They were quite straightforward. And then we found a reproduction number. And this had two components. One is contributions from symptomatic individuals, and the other was contributions from asymptomatic individuals. Right, so the R naught fell out quite nicely. And as I said, we know R naught, right? R naught was 2.35. And well, I know many other things, right? I know the campus population. I know the P here, the fraction of asymptomatic individuals. I know the recovery rate. What I don't know is the eta. So I don't know the relative transmissibility. I don't know alpha, the recovery rate for the asymptomatic individuals. And I don't know beta, the transmission rate. right? So what I'm going to do is I'm going to use things that I do know to basically get some idea of things that I don't know. Right. So let's rearrange R naught and determine likely beta values. So if I basically sub in all the numbers that we do have, then kind of here's the average beta, if you will. But of course, it depends on other factors we don't know. I don't know how much better the asymptomatic individuals are recovering, right? So that's the alpha. And I also don't know how much worse they are at transmitting. That's the eta. Right? So what we can do is we can say, well, let's consider a bunch of scenarios. And I think this is the point where mathematics is really helpful, because if I wasn't doing math, I would have to say, well, I don't know these numbers, so let me go and find them. And that would take time and effort and so on. We don't have the luxury of time and effort at this point because the university wanted answers immediately. So we can do all the things, right? We can run multiple scenarios. So that's exactly what we did. All right, so let's run a couple of possible scenarios. Let's consider some extreme cases. So for example, what if asymptomatic individuals are identical to symptomatic individuals? Right, so there's no difference here, right? So that means n and alpha are equal. In fact, it doesn't even matter that they're equal to 1 here. It just matters that they're equal, because of course then they will cancel from that fraction. So in that case, beta is 2.797 times 10 to the minus 6. Well, so there's a possible estimate for beta. Another extreme case is that asymptomatic individuals don't infect anyone, right? So if they don't infect anyone, right, well, that means the disease is being driven by the symptomatic individuals only, right? And in this case, beta would be 3.37 times 10 to the minus 6. So we have a larger beta here, really because what we're doing is we're pushing all the transmission into a smaller group, right? So the smaller group of susceptibles is now doing all the work. That's why the beta is larger, because they would have to be spreading, like essentially the per person infection would have to be larger. Another option is to split the difference and say, well, what if it's somewhere in the middle? So here's a kind of test case. What if asymptomatic individuals are 50% as transmissible as symptomatic individuals, but they recover twice as fast? Now, what I'm going to do, so that gives us a beta somewhere in the middle. So what I'm going to do is I'm going to look at the cases 1 and 2 first, because they give us the two extremes. Right, so that gives us kind of a low estimate beta and a high estimate beta, and then we can see what possible outcomes come from that. But later I will come back to that third case and look at a likely case scenario under slightly different circumstances. All right, so, oh yeah, this picture here, this is the University of Ottawa, for those who haven't seen it. This is us in winter, and I think most of you in the Philippines may be having a little bit of a gasp, because I had much the same gasp when I saw it, because I come from Australia where it's nice and warm. But I have learned to adapt to Canada, and I skate to work on this canal. It's lovely and beautiful, and it's very hard to get pictures of this because the university doesn't like to advertise the fact that they're very, very cold, because they think it'll scare people away, whereas I think actually it's a selling point. I think why not? Why not advertise that you can skate to classes? Sadly, we can't do that now, but that's by the by. All right, so back to our simulations. All right, what we wanted to do was we wanted to test our different values of beta, and let's find some possible long-term outcomes. And the two particular cases we're going to look at is, what if we don't do anything? So that was one possibility on March 12th. And the other was, what if we cut contact rates by, say, 50%? Right. So this was another possibility. Of course, we know that in truth, what happened after March 12th, later in March, was we cut contacts by quite a bit more than this. So I will come back and talk about what happened in reality. But this was what was done at the time. And so, there was discussion of, should we go to like a 3-day week, for instance? Should we start reducing classes? And in the worst case scenario, so the highest beta that we have, if we don't have any intervention, then you can see this is on a log scale. So the red is the symptomatic individuals. That goes up to 10 to the 4. And the first death on campus is 115 days after the first symptomatic case. So let me throw the larger graph up here. So the small box in the inset, that's the same as the previous page, except for the full scale. And you can see that we would peak at 6,000 infected individuals. The first death is 115 days after the first case, and the overall death would be 63 individuals dead on campus. And what you also see in the full graph with all the colors, the blue, for instance, the susceptibles, they almost entirely go down to 0. Right, so you lose a lot of susceptibles. So what's happening is there's an exchange. Most people are getting infected, and then the vast majority of whom recover. That's what you would expect on a campus. So you have a kind of classic epidemic curve that's happening in the red. That's kind of an infection wave that you would see in many classic textbooks on diseases. So that all seems quite reasonable. But of course, you have to go through the infection to get there. Right. So this is our kind of worst case scenario. So is 63 deaths too many for campus? Is 6,000 cases too many? That's not really my call. That's kind of political leaders' case, but at least we can present the options. Okay, so what about the best case scenario, right? Well, if we choose the better beta, then you can see it's a much lower peak. I haven't quite got to the peak yet, but the first death appears 150 days after the first case. So in the full amount, you can see, oh, actually, sorry, the peak is slightly higher in this case, sorry, because in this case, it's being driven by the symptomatic individuals. Right. So in the best case scenario, you would actually have more infections overall, but you actually end up with less deaths. But it's the same order of magnitude, right? So we're talking about 7,000 cases, right? 58 deaths, first death appearing 150 days after the first case. And again, a similar kind of exchange of susceptibles. Not quite as many people are infected, but majority are. All right, so those are the cases without intervention. So let me just sum up. All right, so we would see the first death about 115 days after the first symptomatic case in the worst case scenario, with eventually 63 deaths, or we would see the first death 150 days after the first diagnosis, eventually leading to 58 deaths. All right, so that's kind of the do nothing case. If we halve the contacts, right, then the worst case scenario, you see quite a big reduction here, right? So we've reduced from 10 to the 4 to 10 to the 2, and the first death appears much, much later. It's like 450 days later, right? So in the graph, you see that the peak is now 700 individuals rather than 6,000. So that's great. The number of deaths long-term would be 25. That's a significant improvement. And remember, this is the worst case scenario with half the contacts. But I think the other thing to note from here is that many people do not get infected, right? The blue susceptible curve, it doesn't even go to halfway down, right? So that means a lot of people are not getting infected in the first place. All right, so what about the best case scenario with 50% contact reduction? And here we see, well, now we're kind of talking 10 to the 1 cases, and the first death is appearing kind of about, it's 1850 days after the first case on campus. So that's quite a long time. So here we're talking 25 cases overall, the first death appearing 1850 days later, and 5 dead individuals overall. If you look at the blue susceptible curve, you see that most people are uninfected, right? The infection basically doesn't come through if you halve the contacts. Now, we did significantly more than that. So in truth, so this is kind of what we're probably looking at, right? I'll also put up the Ottawa numbers in a bit. I will just say, though, this is a very long time scale, right? This is in days, and we're talking 5,000 days is many, many days. So in practice, we would have probably have to refine our model because there would be lots of changes. So I'll talk about that towards the end. Okay, so just to sum up, if we have high transmission, then the first death occurs 450 days after diagnosis, leading to 25 deaths. If we have low transmission, the first death occurs 1850 days after the first diagnosis, leading to 5 deaths. And what we see is reduction of contacts is very critical, right? It really changes things in all cases. All right, so what happened with this model, right? I gave it to the administration very late in the evening on March 12th. And so on March 13th, so one day after receiving them, or really as soon as they received it, what happened? They closed campus entirely, right? They said, no, we don't care about this 50%. We are closing this down to 0, or at least as close to 0 as they can. It remains closed, except for essential research. So for example, some labs that can't be left unattended. And summer 2020, which I've just finished teaching, fall 2020 and winter 2021 are all online, right? Including next winter. So we basically said we're guaranteeing everyone is online. That's in part to give some certainty to international students so they can make plans accordingly. But also, I think it's not a bad idea, right? And I will certainly say now, having taught 1.5 courses online, I don't see the problem here. I don't know why other places are not doing this. I mean, some Canadian places are doing it by semester, and most of them are staying closed in the fall. But I think other places definitely should be closing down. I don't really see the point of keeping it open. And what we see from this is reduction of contacts really matters. And the university is a big mixing pot, right? There's lots of people moving around, having close contact with each other all the time. That's something that I think we can easily, take care of. All right, so what about since then, right? So since March 12th, well, more information has come to light, so we know some more things. Also, we very much changed our patterns of behavior due to global lockdown, right? So there've been no deaths on campus since, well, that's pretty much to be expected, except there actually has been a case on campus, right? In fact, there wasn't until I was preparing this talk. This was discovered on July 20th that there was a case in the support staff who was attending. It was one of the labs, I think. So they had to quarantine that person and also anyone who was working in the lab with them. So in a sense, you could think perhaps the clock has started, right? We've seen our first case on campus. Now, it's not under the same conditions as it was in March, but nevertheless, how long are we talking until the first death? I mean, one might hope that it never happens, but realistically, it may well, even with the reduction that we have, right? So it may take a long time, or we may just get unlucky. All right, so just to pull back a bit out of campus and talk about the city of Ottawa. Right, so Ottawa is the capital of Canada. It's a mid-sized city, and the infection has followed the typical age distribution. There were significant infections in hospitals, in retirement homes, and long-term care facilities, but not very many in the community. The lockdown happened, pretty quickly, pretty efficiently, and it's been pretty good. Here is the data. So this is the data as of last week or so, right? Let's get the mouse going here, right? So I think if you look at the graph here in black is the institutional outbreaks. So you can see we had quite intense outbreaks in institutions. The blue dashed curve, that's the sporadic outbreak. So that's sort of people bringing it in from elsewhere and so on. And the green, which is right at the bottom, that's the community outbreaks. So you can see there was some community outbreak, but very low numbers early on, and then not much else since. In terms of ongoing, the number of deaths has been very static at 263 for quite some time now. So that has not changed. Actually, I checked today and it's still 263. So the deaths is very flat. The number of cases is rising a little at the end, but well, who knows what is going to happen eventually. Of course, the latest data is always subject to revision. The age distribution is pretty much what you would expect, right? It doesn't really affect younger people that much, but it affects older people quite a bit. There's quite a gender disparity, which was a bit of a surprise to me. I don't know why it's so skewed, so the 60-40. I'm sure there are all kinds of explanations we could figure out for those. So that's where we're at the moment. So functionally speaking, Ottawa's first wave has ended. Right? So we have a total of 244 cases, 263 deaths. That's out of a population of 1.4 million for a kind of mid-sized Canadian city. Sporadic cases peaked in mid to late March at 27 cases per day, and a much larger outbreak in long-term care facilities peaked at 93 cases per day in April. So the last thing I'm going to consider is what if we reopen campus, right, with appropriate caution? And so there's been some discussion about this. So for example, we have masks, we have partial remote learning, right? Now, one of the knock-on effects here is, of course, contacts with symptomatic people would be lower, both because we're being more careful and also because individuals would be isolating if they had symptoms. And this might offset their higher rate of viral shedding compared to asymptomatic individuals. So we could revise that, right? So for campus, we said, well, people are under 70, so let's use the lower death rate. We might do a similar idea for asymptomatic individuals, right? So younger people are less affected by the disease. So if they're going to be infected, they're probably infected in an asymptomatic way. So what we can do is we can have a ratio, say, well, the population death rate to population symptomatic rate, we could match the campus death rate, which we'd adjusted to the campus symptomatic rate, and say, well, that gives us a way of finding the campus symptomatic rate. And if we do this, we find that in that kind of like mid scenario where we had recovery happening twice as fast and transmission half as good, we would have 97% of people being asymptomatic, and the beta here would be like 10 times 10 to the minus 6. It would have to be much, much larger because only a very few individuals are doing most of the transmitting. And in this case, if we run the numbers as before, then what you can see is, yes, most people get infected, but the total number of cases peaks at 300. Right? That's quite a ways down from 6,000. This is the worst case scenario. And the number of dead individuals is 2, right? So that doesn't seem so bad. You can also see in the larger graph, you can't really see the red here because the red peak in the big graph has been replaced with the kind of light blue one for the asymptomatic individuals. So this is a disease largely driven by asymptomatic people on campus, right? So we've peaked at 300 instead of 6,000. The first death is predicted at a similar time, 127 days versus 115. Total deaths, though, is kept at very low numbers, and the other cases produce similar results. All right, so one of the long-term predictions we said was for 5,000 days, and I do want to stress I'm not suggesting lockdown remain for 13 years. That would be quite intense. It's really up to political leaders, and I guess university leaders, to decide how many deaths on campus might be acceptable. Right? Is it 2, 25, or 63? That may change under different circumstances. The actual reduction due to lockdown was almost certainly more than 50% among students, but it's probably heterogeneous. right? For example, if students are essential workers working in grocery stores and so on, and they may take on more of these jobs if they're not needing to be on campus. So they may end up having more contacts as a result. So that's certainly possible. Some of the limitations of this was it was a snapshot in time, right? The data was what we had on March 12th. The model does not consider vital dynamics, so no influx of new susceptibles, no deaths due to other reasons. It's probably going to remain true that there are no new susceptibles, but university policies have changed due to lockdown, right? And so who's coming to campus? That's a very good question, right? It's right now it's not too many people. That may change over time. For example, we might have fewer international students. I know I have a master's student who went back to Korea and is doing her master's from there, including TAing. She doesn't mind TAing at 3 a.m., so that's fine. Also an increase in distance learning. So lots of different things will change the makeup of the population. So we'd assumed mass action transmission for our transmission rate. This assumes individuals are well mixed. This assumption may not hold in future, right? So we've reduced the number of contacts, but also the strength of their interactions, so that you may have, fewer contacts, but you also may have some really intense contacts with a very few people. So if we were to update our model, we might change the nature of the transmission. We also assumed that recovered individuals were immune to reinfection, which was the thinking at the time. We now know that is not true. It's much more complicated than that. So that would probably need to be updated for the next step. All right, so in summary, some of the benefits of this model were its rapid development, its flexibility in considering multiple cases where data was lacking, the ability to directly answer questions posed by the university administration, especially in kind of a blind panic. So what we've seen is the role that models can play during a fast-moving pandemic. We've shown the power to make predictions and illustrated their ability to inform policy when linked to decision-making processes. So in conclusion, we've illustrated the interface between theoretical mathematics, numerical simulations, real-world data, and human behavior. By modeling the disease during the very early stages of a pandemic, we can see a variety of potential scenarios. They can be assessed quickly using the information that we had at the time, and decisions can then be made by the administration armed with useful predictions. Okay, so this has actually just been published in proceedings of the SummerSim 2020 conference, which happened last week. So if you're interested, you can find that on my website. You're welcome to either click on the link or type the link, I guess, or look at the QR code. They take you to the same place. So I will say thank you very much. And I will come back for questions after the next two talks, I believe.
Thank you, Robert. So for the participants or audience, feel free to type in your questions in either the Zoom or YouTube chat box. We'll take the question and answer after the third talk. For our second speaker, Dr. John Frederick Tapia is an associate professor in Chemical Engineering Department of De La Salle University. He earned his PhD in Chemical Engineering at De La Salle University and was a postdoctoral research associate in university last year. So his research interest includes process systems engineering of low carbon energy systems, mathematical modeling of biomass value chains, specifically oil palm value chain. And he's also interested in GIS-based analysis of suitable lands for oil palm. He has around 20 Scopus Index research articles and has an H index of 8. Without further ado, let's all welcome Dr. John Frederick Tapia.
Hello. Thank you for that introduction. So, is my screen visible in the on Zoom?
Yes, we can see it, Fred.
Okay, so I'll start with well, what I'm talking about today is about the ternary diagram visualization of epidemic progression. So specifically for COVID-19. So in the recent news here in the Philippines, we have been tracking on how many cases have been added daily, how many have recovered, and how many died due to COVID-19. So we thought of some visualization in which we combine these three variables and plot it in a ternary diagram. So just a short outline of my presentation. So I'll discuss about the epidemic progression in COVID-19, which I'll present what's the limitation of the curves or the epidemic curve that we use to track the disease. There's some indicators for epidemic progression, including the rates and the numbers itself. And then I'll discuss or demonstrate the ternary diagram methodology. And as the highlight of this talk would be the different ternary diagrams, which includes an illustration of some selected countries, a scatter plot, the global data as of mid-June, the time when we are writing this research study, some select Southeast Asian countries. And recently, I just tried to determine what's happening, especially in the country, in the Philippines, and specifically in the its main region or main capital region, which is the NCR. So for the NCR plot, I'll be presenting what happened during the lockdown on or the enhanced community quarantine lockdown. And after the lockdown has been, or after the lockdown being loosened or becomes a general community quarantine, and some advantages, and then some advantages for the ternary diagram. So the global or the disease has caused a major health crisis in which up to this date we have around 16 million cases worldwide with 645,000 deaths. So with the absence of a widely available vaccine and viable and widely available vaccine has made countries to rely on interventions such as lockdown. So as you can see in this picture, we have in the Philippines what we call a community quarantine, and we classify regions depending on the strictness of the community quarantine. Now, as the lockdown period gets longer, for example, here in the Philippines, we have around 3 months or almost 4 months um, community quarantine. The effect on the economy increases. So, how do we visualize the epidemic or specifically COVID-19 in a specific region such as in the Philippines or in the national capital region. So we keep track using an epidemic curve as shown, and it relies on the number of cases. So it is reliant on the how many cases are added or how many cases in total on a specific day. But then the limitation of the epidemic curve is testing. So in the red curve, we cannot observe this if we are hindered with a limited testing capacity as shown. So what are the indicators that we have for the disease outbreak? So I've written here 8 uh, indicators for disease outbreak. So we are quite familiar with the reproductive number as to how many individuals can be infected per individual or per infected individual. The cases per million of population, which um, indicates the spread of the disease in a particular region. The doubling time, which denotes how much time is needed or how much time is required for the number of cases to double. And some familiar indicators such as the number of active cases, fatalities, recoveries, confirmed cases, and cumulative number of cases. So for our visualization, we focus on the three indicators, the number of deaths, the active cases, and recoveries. All of these are cumulative on a specific date. So, what is a ternary diagram? In disciplines such as engineering, we are using ternary diagrams in different applications. So, if we are given with three variables, where the ratio of the three variables is important, we can describe it in a ternary plot as shown here. Now, in say geodetic or civil engineering, which focuses on soil texture. The percentage of sand, clay, and silt can be plotted in a ternary diagram, and the soil texture can be classified depending on the region where the point is located. And then we in chemical engineering we use ternary diagram to model liquid extraction or extraction of um, organic compounds using solvent in a three component mixture, in this case ethanol, water, and ester. So in epidemics, so we just like what I mentioned, we use three um, variables to be plotted in the diagram. So how does the ternary diagram works? So the starting point of the ternary diagram is when the first infected individual or the first case appears. So that would be plotted on the origin. So this would be 100% active cases. And then this point, the point on the vertex above which shown here is the uh, signifies that 100% death, and in the lower right signifies the 100% recovery point. Now our goal reach the is to actually reach the line where there are no active cases appear. So this is the orange line highlighted in this slide. And then, for example, we have for the first point, we have 1,000 cases, 200 recoveries, and 50 deaths, which can be translated into 80% active, 16% recoveries, and 50% death or 4% death. We can plot this by locating these points or these percentages into the ternary diagram. So in these three lines, and then the intersection can be identified as our first point. Another demonstration would be, for example, there are more recoveries and somehow more deaths. Like in this point, we have 1,500 active cases, 800 recoveries, 200 deaths, or 60%, 32, and 8% respectively. So we again identify the percentages in the lines, and then for we determine the intersection of this line, and that would be our second point. So this is how you plot the reports or the reported cases in a ternary diagram. So as to illustrate this plot. So I presented the following ternary diagrams. One would be for the trajectory of selected countries as scatter plot. So that would be for my illustration of the approach or visualization. Then the global data as of mid-June containing all points or in cumulative numbers around mid-June. Then some selected Southeast Asian countries, which is presented as a line plot. And then for the latest one, which I had compiled last July 18, for the plot for the National Capital Region in the Philippines before and after the enhanced community quarantine. So this data, especially the first three, were obtained from the Center for Systems Science and Engineering at Johns Hopkins University in the link below. Now, the NCR data was obtained from the DOH tracker, which I accessed July 23. And the data was plotted in Python using the ternary package, which I obtained in GitHub. So here's an illustration of the plots for select countries. So I've chosen Belgium as it has the highest death rate at the time of writing this paper or this presentation, and then I included some developed countries like Spain, Italy, South Korea. So in this case, you see how the plots were forming a line wherein at some point the lines were really spread out. In the case where the number of recoveries is from, say, 30 to 55% for China and South Korea. And then for some, like in Spain and Italy, at around 40 to 45%. So the scattering of the lines signifies the rate at which the number of cases, the number of deaths, and the number of recoveries progresses. So the more scattered it is, the more um, in a curve fashion, the more scattered the line is, or the points is, um, the more or the faster the changes happen. So this is for the some of the selected countries. Now the points at the end of the curve signifies the latest data as of the visualization. So this is around mid-June. So ultimately, you can see which countries have already on or near the no active case line. So this is somehow signifies that how they are, how their response is working for their country. So here's the global data as of the mid-June. So as you can see, most of the points were located below the 20% uh, death rate, which is important because which verifies that the disease has a which verifies that the disease has a low death rate. Now, if we zoom this in, so if we um, zoom this in, so there. So you can see which countries is has been or is on the or you can see the distance from of the countries for in the no pandemic or the no active case line, which the Philippines at the time of this plotting is far or is very far from this line. And then if we zoom in for some select countries, you will notice the trajectory of different Southeast Asian countries in which only the Philippines has experienced something like a more of a backward direction as um, signified in this plot. And then later the I will show the plot for NCR, which also contains this kind of um, trajectory or um, this line. Okay, and then I tried to actually plot the number of cases, deaths, and recoveries for different cities in NCR. But unfortunately, when I access the website of Department of Health, they only present the data for the NCR. So what happens during the ECQ is shown in this plot. So we are progressing from somewhere a recovery rate of 5% to around 35 percent. Now, what happens during the general community quarantine is that we experience more of a forward approach or a forward direction. But at around June 20, the trajectory starts to move backwards until to a point where we have around 30% recoveries out of the cumulative number of cases. And then on July 11, it starts to um, to move forward, in which at July 30 we experienced the highest number of recoveries in that in a single day. So we show or resume that in this case we have a progressive um, direction during the enhanced community quarantine and a somehow um, for a short or for a certain period we move backwards. Now the good thing about what happened in NCR is that the death rate is decreasing, so it to around 11% of the total number of cases at the beginning. We had to around 4% at the latest. So what are the advantages of the ternary diagram? So as I've shown in this um, in this in the illustration, so it presents a two-dimensional progression of the epidemic, which shows a simultaneous plotting of number of cases, number of recoveries, and number of deaths. Then we can also compare the different regions in terms of their progress from since we have a um, more of a specific target in this ternary diagram. And then the spread of successive points along the given trajectory is indicates the dynamics. And finally, it provides a progress bar. So like what I've said, we have a certain point of origin and a certain point of success for the epidemic or in this case in COVID-19. Some conclusions. So the ternary diagram actually gives the some insights for planning as we can see how we are doing in terms of our interventions, lockdowns, or if there are available antivirals and some other intervention. So I've already given the four main advantages of this cover the epidemic curves. Then this can be used for insights for prioritizing facilities and financial aid or another measure. So if you have question after this talk, just send me an email to this email address as shown. So thank you very much for your attention.
Okay, thank you, Dr. Tapia. But for now, if you have questions, you can type it in the group chat box, either in YouTube or here in Zoom. Um, for our third speaker, Mr. Robert Neil Dion. Okay, he's also Robert, like our first speaker.
Yes.
He's a PhD student in the School of Public Health and Community Medicine of the University of New South Wales, Australia. His thesis is on economic evaluation of alternative vaccination strategies against pertussis in Australia. So he's a statistician by training. He obtained his BS and MS degree at De La Salle University from the Mathematics and Statistics Department. Robert is a biomathematician, biostatistician, mathematical epidemiologist, and economic evaluation specialist. He already has at least 10 Scopus Index international journals, and he has experience on processing and analyzing large longitudinal health-centric data sets and electronic medical records and developing statistical, mathematical, and economic models applied to policy and intervention analysis. So currently, he's actually actively involved in some COVID initiatives such as Leads for Health, Security and Resilience Consortium, and the World Health Organization Regional Office as a contributor to measuring epidemiological metrics. Without further ado, let's all give a virtual clap to Mr. Wala, hindi pa siya.
Yes. Hindi pa po. Yes, anyway, I am now sharing my screen. I hope you can hear me well and you can see my screen. Okay, so just a bit of a background. This work is part of the technical advisory working group that my supervisors are involved in providing technical assistance to the WHO Western Pacific Regional Office in their pandemic response, especially against COVID, and in particular working for the countries Cambodia, Malaysia, and Philippines. But I personally is only involved in one particular aspect, which is on RT, basically estimation of the effective reproduction number, which I will tell more a bit about later, and specifically only for Malaysia and Philippines. So yes, so essentially this talk will be about more about demonstrating what tools we can use, or what is the tool that we are currently using and how we are trying to develop it to better produce or nowcast, in other words, nowcast and hopefully later on forecast RT in the context of measuring the effectiveness of NPIs, which in our case are only lockdowns in controlling COVID-19, and just showing Philippines as our case study. So before I start into that, okay, so why is it not moving? There you go. So before I start into that, just special thanks to all the all the groups that we have been involved, or I've been asked to who have been collaborating with us. With special mention to Lynn and Laila of the WHO Philippine Country Office, who has been our data custodian, who has been supplying us Linely's data, although a little bit late, but at least it's on a fortnightly basis, and especially the Leads Consortium, which I am part in, from which I've gained a lot of insights just by hearing the conversations, exchanges, and everything. So yeah, as mentioned, I think there's not much more that I need to there's not much background that I need to talk about COVID, because that's already been tackled by both Robert and John Frederick in their earlier talks. So basically, what I would just want to show here is that this is a snapshot of, or rather, a snapshot uh, of one of the things that is available in the Leads website, which I have listed below, and that we have been monitoring for the Philippines, which is the here what you will see are the case numbers, or the confirmed case numbers, as well as the number of deaths, rather the active and the confirmed cases, rather, sorry. So this is taken 7 days before, when I was starting to prepare these slides. So one thing that stands out here, rather, and as of yesterday, if I'm not mistaken, we have already, or at least Philippines nationally has already surpassed the 80,000 mark of confirmed cases in total since the beginning of this epidemic. So what do I want to highlight about this? So if you would see in this graph, there have been particular measures. There have been particular there are key dates wherein we try to implement certain measures to try to contain the spread of this virus, beginning with an enhanced community quarantine, and supposedly when mass testing has started, and little by little relaxation of these, or lifting of these uh, lockdown restrictions. But despite all these, we are still seeing market increase, not just an increase in the number of cases, but rather also an acceleration, at least in the tail end, an acceleration in the number of confirmed cases that we're having. So basically that brings the question about how effective are these lockdowns, essentially, despite having one of the longest lockdowns in the world, why are we still seeing increases in cases? So that is what we are trying to answer in this particular project. And in particular, not the entire Philippine region is put in the same level of community quarantine at a certain given time. Actually, it is varying across different regions, across different cities, municipalities, LGUs, etc. And this is a table that is provided to us by the WHO country office in the Philippines as of 30th June. And obviously, this has been updated. I think last would have been 15th of July. But bottom line is, while it's not surprising to see that the more restrictive restrictions are in place only for those regions which has highest numbers of cases. Uh, One thing that also stands out is that these regions, or these cities, are mostly urban or highly urbanized. So So that goes back to the question: how do we assess, or at least how do we have an idea of how effective these lockdowns are? So one thing that really gained one measure, epidemiologic measure that really gained interest all throughout this pandemic is the reproduction number or not. And obviously, if you are to translate this into a real time indicator, we, it is your effective reproduction number, or we would term RT. So just how do we define RT first? So RT is clearly defined as your estimated number of new infections caused by an infectious individual in a population where there are already other people who are not susceptible, who are no longer susceptible. So that is the key difference with the basic reproduction number or not. So given this terminology, so in principle, this should be useful, at least in providing insight into the level of transmission and changes in transmission in potentially near real time, because this is the indicator that follows the number of cases as they come in on a, well, it can be on a daily basis. But however, one thing about, while while that while this RT is estimated based only on cases data, obviously, this relies on the quality of the cases, or rather the reported cases data, which we know have some inherent biases. Which, for instance, one thing that is apparent with COVID-19 is that there has been delay in infection and in onset of symptoms, and then further reporting delays, which is your right censoring or truncation. And from time to time, you will also be missing out reporting of cases. And in the cases data, you will not be able to reflect, or you will not be able to see which of these cases are artificial, which could have been brought about by increased testing capacity, or contact tracing, for instance, and or is an actual increase in cases due to more active transmission. And obviously, one thing about the reproduction, one thing about RT, if you are interested only in measuring local spread or community spread, you have to isolate out imported cases. So that is what we tried to do in this project. Now, take note that that what we have now is by no means compared to a more comprehensive compendium of RT statistics that is already developed, or currently being developed and updated on a day-to-day basis by Dr. Peter Kaiton and his team, including Mr. John Hill Sarmiento, uh, his team with UP. I think it's UP and COV. They've been producing daily statistics of, part of which is the RT estimation, but it is based on EPSTIM. And it is comprehensive in the sense that it covers a lot of LGUs. So this is by no means uh, this by no means replacing that, but rather what we would want to highlight here is that how we can use uh, EpiNow, which is also based on EpiSTIM, but with some improvements, especially in trying to incorporate the delay in diagnosis and the reporting delays, and from which we can right then and there separate out imported from local cases, by which not only RT is estimated here, but rather uh, it can also, as part of its summary table, it also gives us the rate of spread, which in turn is converted into doubling time, etc. Now, some of the assumptions that we have to make here is that first, the default serial interval is used as well, which, and the prior estimate for R naught is also set, basically the same as with what you have with FPSTIM. And just to let you know, since this was, I have prepared this slides, I think, a week ago. The latest available data provided to us, line list data, by line list, it is actually individual listing of the data, with as much as possible. I think more than half of them had uh, the actual onset date, etc., etc. provided to us by our data custodians from the WIPRO office and DOH office would be the 5th of July. So it has been more than 3 weeks since, and we're expecting that new data will come in by the end of the week. And one thing to do is that as in any RT estimation methodology, it is assumed that case counts are actually more or less complete and they are reflective of the incidence trends. Now, one thing about estimating RT is that we are hampered by minimum number of cases or the case limits that we have to have in the last 7 days before a robust estimates are provided. So not only that we must have sufficient cases over time, but rather we should have sufficient cases over the last 7 days to have been recorded for this to work. So now, why 7 days? It is because EpiEstim is using a 7-day window for the RT estimation. Now, one thing about EPI now, as I mentioned, is that it automatically adjusts for the reporting delay by using a delay distribution function, which is derived from your line list data. So if your line list data, as we have seen, as I have reported here using our latest data available, has now a median reporting delay of 10 days. So what essentially happened is that any RT estimate for any particular day is back the data was well for that particular data. So for instance, so that is the reason why, if you will see later in my plots, even if latest data available was for 5th of July, it the RT estimated for that date is actually reflective of the conditions 10 days before, which is 25th or 26th of July. So essentially what we're doing here is that we are producing nowcasts to 10 days prior to the latest date of data, and then from that date, um, we are essentially conducting forecasts up to a further 14 days after 5th of July. So that's also one thing about EPI now. Based on a TBATS model and ARIMA models, they are producing forecasts of the RT from which, after forecasting RT, they will use the RT forecast to forecast the what would have been the number of cases, confirmed cases moving forward. But we haven't explored much yet of these forecasting yet, so I won't be able to talk about it as much. So to demonstrate, this is what we have for the Philippines in general. So um, as you would see from when we first started with this epidemic, I think early in March, in fact, early March, it is not surprising to see that our RT is more or less from an high of, actually it's about close to the R naught value of 2.2, and from since on, when the ECQ was first implemented, I think 15th of March, at least for the National Capital Region and many of the regions surrounding NCR, it has taken RT down to levels around 1. But it is not surprising to see that because of when by late June and even until now, actually, we are seeing an average of 2,000 confirmed cases every day, which is higher than what has been happening before the last week of June. It is not surprising to see that RT, or at least our estimates of RT, will be above 1. Oh, just to give you an idea, just to give you more details on this, the RT values are in this panel plot B, while the panel plot A on the left is your daily confirmed cases, and the line plots and the shaded regions are the estimated values coming from the EpiNow package, and the gray plots are your forecasts. So the middle block solid line is your mean estimate, while the darker green shade is your 50% credible interval. Yes, credible interval, because they are based on the Bayesian framework, and the lighter green shaded region will be your 90% credible interval. So this is for the Philippines. And In comparison to EpiStim, which is the more commonly used tool today, it's not surprising to see that we have essentially the same, more or less the same shape, except that with Epi now it is much more smoothed. And one thing that you would notice here is that if uh, estimates of Epi now is shifted to the left compared to EpiStim just because of that reporting delay that we have introduced. So what does it mean? So it is not surprising to see that, say, what EpiStim estimates as for today is actually EpiNow's more or less estimate 10 days before, because of the fact that we're using a 10-day reporting delay as our rather 10-day median reporting delay as our now casting date. Now, one other thing about Epi now compared to EpiStim that you would notice is that with EpiStim we have tighter intervals, because from while Epi now has, well, um, wider intervals, per, prob- perhaps suggesting there are more uncertainties in our estimates, just because with Epi now we are also considering, what do you call this? Considering uncertainties brought about by the reporting delay function. So that's the thing. But essentially, they tell the same picture, except for the aside from the numbers being different. If we just focus on the qualitative interpretation of these numbers, rather qualitative interpretation of these plots, they essentially tell us the same thing. So going further down, we can also conduct estimations by regional or subnational levels. Here we have it for Manila, Metro Manila. And as you can see, it essentially tells us almost the same picture as that of the national estimates. Not surprising, because I think more than 50% of the confirmed cases nationwide is from Metro Manila. And in fact, part of Epi now is that it is able to provide you these plots where it has an estimate, a probability estimate of which cities or LGUs, whatever, have been experiencing increasing or would have likely been increasing or maybe decreasing in the certain number of cases based on the distribution of their RT as we have estimated. So it appeared here that Quezon City would be one of the highest back then. Back then, we have estimated Quezon City to be one of the cities to have been experiencing or more likely to experience increased number of cases, so on and so forth. And we can also do the same thing for some regions, and I have included here some regions which are of particular interest during the time that we're doing this, because we're seeing increases in these regions. So for example, region 4A, the Cavite, Laguna, Batangas, Rizal, and Quezon province. um, while at some point when early on it appeared that they are not experiencing sufficient transmission, COVID-19 transmission, but lately, due to increased cases as well, uh, we have seen spikes in a rather increase rather in their RTs, and of particular concern is the Central Visayas region, which includes Cebu, wherein at some point it has now experienced RTs significantly greater than 1, in particular Cebu City. At some point, I think in around mid or to late May, which would have influenced, which we think have influenced the decision to have the city revert back to an ECQ, I think by mid June. So what does all these tell us? Um, in our technical report, what we actually mentioned there is that based on these measures, it appeared that initial lockdowns have successfully mitigated the exponential growth of the epidemic early on. Let me reiterate that it is early on, or in other words, it has in some ways it was able to slow down the growth of the epidemic, especially by April or May, something like that. And with RT hovering around 1, why are we able to say this? It is because RT has hovered around 1, which more or less led to more stable case numbers. However, with RT increasing just even slightly above 1, it may lead to large case numbers, as we have seen in the more recent days in the data that we have in the regions that we have plotted for, just because of this operating under exponential growth. So given that it is experiencing exponential growth, even just an increase of, say, from 1 to 1.05 or 1 to 1.10, you are expected to see almost, I think, doubling, or not really doubling, but almost 10 to 20% increase in cases as well. Now, so what do these tell us? Bottom line is, while we were able to successfully mitigate the exponential growth, these have not been sufficient to entirely eliminate the infection or even prevent regional spread outside of Metro Manila. But take note, we should exercise caution in interpreting these numbers, because what I have pointed out a while ago is that this does not reflect yet testing testing capacity or increase in testing capacity. And also caution that in all these RT estimation, they are by no means an absolute measure of the effect of lockdown, just because the model, or rather the RT estimation framework, was not really built, or was not really designed to describe and isolate only the effects of the lockdowns, and that because of time delays, or basically a distribution of time delays, would lead to cases being spread out over time, even when the intervention occurs. But the main takeaway from all of these is that we advise against premature lifting of restrictions. We can do this on a go about this on a day-to-day basis, and easing as we see fit. But basically, with premature lifting of restrictions, cases we are anticipating that cases will rise, especially in high-risk urban areas. So for future directions, one thing that I have noted a while ago is that this EpiNow framework, only works with sufficient sample size or sufficient number of cases. In fact, by default what we're doing is that uh, we see that it's only able to produce robust estimates if we have 20 new confirmed cases over the span of the last 7 days for RT estimation to work, and further another 40 cases for forecast to work. So what happens if we have LGUs, or what happens if we have areas such as most of the regions? If we go at subnational levels for Malaysia, what can we do now when the number of cases are declining? So one thing that we're currently doing is we're exploring a more advanced tool, which the website I have put here, which is estimating RT, but in the context of local transmission potential. So what does it mean? So when there is sufficient epidemic activity, this is similar to the RT that we have now. But in the absence of sufficient epidemic activity, what we are actually trying to do is that we're trying to put in some measures, like say mobility data, so on and so forth, for which we will try to project what would have been the RT had there been also what would have been RT based on these proxy measures, and measure basically the probability of transmission or your transmission potential. So that ends my talk. Thank you very much. And
Thank
yeah, I think I'm sorry. How do
Due to time constraint, we'll only take 1 to 2 questions for each speaker. And for the speaker, kindly also try to answer them short, precise, and clear. For Robert Schmidt, the first question was from YouTube. Okay, someone posted from YouTube. It's from Dr. Raymond Tan. If COVID-19 severity is a function of viral load upon infection, then cases will inherit features of previous cases. Can such an effect be integrated into an epidemic model?
Yeah, that's a great question. I think that in some sense it already has. Certainly, I would say when I was designing the model, I drew on my experience with other models like for HIV and so on, where infectivity generally scales with viral load. And so in that sense, I think it gives you the structure to design kind of the SAR type models and what type of transmission you're going to choose and so on. But I think also there's probably room for quite a bit of expansion there. That if the disease looks similar to other ones that we know, then we can kind of take some shortcuts in modeling. So yeah, I think that's a great question.
Another question, it's actually from me. Recently, there are news reported, new COVID cases reported after being COVID-free for weeks. So it seems that COVID like incubate, or it appears that there is a delayed aspect of the activation of those who are exposed or after being exposed. So what do you think about it, or can that be also reflected in the model?
Yes. I mean, I think one of the exciting things about a new disease in some ways is like it's such a free for all in terms of the models you design. And so as more information comes in, you can keep layering. This is very much something we did in the zombies. The zombies, of course, is just a fantasy disease, but it was really good for kind of letting you build up different things. And so functionally, with models, what you're doing is you're making decisions all the time. And I think if you decide that this is significant enough, so you decide that, okay, yes, there is a delay in some people. If it's significant enough, you can put in another compartment or you could put in a delay. You'd have to make a decision as to whether this is going to affect everybody or not. I mean, effectively, by putting in a compartment, you're building in a delay. So there's already a delay between immediate infection and then symptoms. That's through the exposed class. But you could put in further delays if you're going to say, well, yes, seems like there's a built-in delay for some people. So I would say my instinct says put in a fraction of people who might have that delay if that fraction is found to be significant. Even if it's not found to be super significant, you could still investigate it. And that's, I think, the great thing about mathematical modeling is you can say, well, let's see what the effect is. And possibly even just a very small number, might have a huge effect, but it might not. Yeah, it's definitely something you could play with.
Thanks, Robert. For Fred, there's two questions. First question is from Robert Schmidt. Okay, he asks, in the ternary plot, why do you start with deaths at 1.0? Shouldn't the number of deaths be 0 initially?
Okay, let me just share my screen again so we can better illustrate this question. So, at each vertices of the ternary plot actually exist two numbers. One is the zero point 0 and the other is 1.0. So for each vertices, the label indicates that the the 100% of that cases is defined by the label. So in this case, you have the origin where the number of cases is, or among the ratio of the under treatment deaths and recovered is that there are 100% active, zero deaths and zero recovery. So that's where the origin starts. So there is quite a confusion, especially in the ternary diagram about these numbers. So the bottom line is the vertex um, means that there is 100% of that what is indicated in the label.
Okay, second question from Dr. Kathleen Abiso. Is it possible to link the epidemic model with your ternary diagram? How do you think we can maximize the information between the two models?
Um, well, the epidemic well for epidemic models, so we are more concerned about the rate, such as rate of the infection, rate of recoveries, rate of active cases. Now, one of the limitations of the ternary diagram is that these rates are not clearly visible in terms of it just present how the plots are being spread out through a trajectory. But if we are to just have the ternary diagram, the plots or the data in the ternary diagram expressed into lines, then we have eliminated the rates instead. unlike when we are using scatter plots. So we can link the information between the two models by their advantages being in a ternary diagram, having um, an indicator of the progress, while the epidemic models giving us the rates or the rate as to how the disease is spreading, how um, the number of cases recovered increases and the number of fatalities increases.
Thank you, Fred. Let's move to Robert Neal. I have a question. So my question is based on the forecast presented in your study, what is your suggestion or recommendation to our policymaker to improve our current situation?
One thing, ma'am, we are not yet so sure about the forecast. If you're referring to the shaded regions, but rather we are more sure about interpreting the estimates or the now casted values for RT. Now, as I have said in my parting slides, what it actually suggests is that lockdowns has been effective. There's no question about that in mitigating the spread. It has not been successful in eliminating the infection, but at least it has been helpful. And given the current climate, what we would suggest is that in the absence of other things that they are currently doing, because we are not entirely in the know of what have is actually being done at the moment, and it's hard to believe in news if you just rely on news. So it's best if they really do have data on all these. But if we are just going to base on the lockdowns itself themselves, what we're suggesting is that they should not be deciding harshly on this, harshly about um, premature lifting of these restrictions, because to be honest, we would be much more inclined to continue the quarantine, at least only from an epidemiological perspective. Let me reiterate that. Uh, at least until we find sufficient evidence that the transmission, the transmission is again reverted back to one, or at least RT is back to one, or transmission has been significantly reduced again.
Okay, another question from Dr. Abiso. Is it possible to identify the optimal time to lift lockdowns?
Um, if it is only based on what we're doing the moment, the answer is no, because that is not what our tool or our estimation framework can do. But if the question is for in general, I think a better model will be your mechanistic model, your SEIR model, which is like what Dr. Smith has discussed. And I think that is where you can play out scenarios, at least to identify when best to lift lockdown or ease out the restrictions. But I think that is still likewise, as with any model, it is not absolute, but at least it gives you an idea on when to best do it. But at the same time, put together all the measures that you have been trying to do to control these pandemic rather.
Okay, there are some more questions, but due to time constraint, we'll end the first half of the session, and I'll pass the floor to Dr. Abiso for the second half of the spiral session.
Thank you so much, Angie. And thank you so much for our speakers. This really is a very interesting topic. And just a few reminders for the next half of the session for our speakers. I know that there's so much information that you can share, but please be mindful of the time just so we can keep our audience as well. I'm sure some of them might have other appointments later on. So let's move on to our next speaker. So the first few for first three speakers, they've really tackled about how to model and how to visualize the information with regards to the infected population. But our next lineup of speakers would discuss other aspects of this particular pandemic. And let's begin with our next talk entitled Reflecting on the Potential Economic Effects of Lockdown in the Philippines Due to COVID-19, Lessening the Impact on the Poor. Our speaker is a full professor and the dean of the School of Economics at the De La Salle University in Manila, Philippines, and her research work focuses on human capital development, poverty and inequality, and on the economics of agricultural development. Without further ado, let us welcome Dr. Marites Chonko. Dr. Tess, you may now begin sharing your slide.
Thank you so much, Dr. K. So are you seeing my slide?
Yes, we can see it.
So I apologize if I can't if you can't see me on video because I'm trying to uh, what's this to maximize the use of the internet. Okay, sorry. I think this should be the first one. Okay, so good morning or good evening wherever you are in the globe, and thank you again for the wonderful introduction, Dr. K. Aviso, and to the Philippine American Academy of Science and Engineering Society for Climate and Disaster Resilience for inviting us in this special session on COVID-19. So I'm going to talk about reflecting on the potential economic and effects of lockdown in the Philippines due to COVID-19. I'd just like to acknowledge my co-authors here for this research work. So Cesar Coloraton, he is a visiting fellow of De La Salle University and at the same time a senior research fellow at the Global Issues Initiative Institute for Society, Culture, and Environment at Virginia Tech in the US. And Dr. Arlene Inocencio is our full professor and chair of the economics department of the School of Economics. So let me just show you this slide, which I showed like a few months ago, right after the lockdown, like 20 days after the ECQ in Luzon. So about that time, I presented this projection on GDP growth showing a V or a stretch V-shaped recovery. This was, of course, assuming we will have a quick recovery in the economy, assuming that we will all cooperate and work together to slow the transmission and that no reemergence of the virus. So there's the economic downturn. Downturn is actually very deep dive here, and then there'll be a recovery right after, a rapid recovery after. But after 3 months of the enhanced community quarantine that was lifted on June 30, 2020, the government started to ease out lockdowns and gradually reopen the economy in Metro Manila and the whole of Luzon. And after that, uh, allowing people to return to work. So I would guess a more stretched U-shaped recovery might be achievable. And that would mean like it could stretch out until 2025 to 2026 before the economy really recovers to its former output level. Now, let me just say that the forecast path shown here does not really take into account the effects of reallocation of resources that the pandemic will bring, has brought about, especially in the labor market. So we all know that there has been an increase in unemployment already, which is around 17.7% productivity losses, labor reallocations, and negative business and consumer confidence growth. And there's also some falling savings. Okay, so now you've seen this already earlier in one of the presentations by Mr. Robert Neal, and I'm just going to show you that this again, just to show you some data on confirmed cases and estimated date of infection. And as you see that R naught or Mr. Robert Neal Young calls it RT, that it's hasn't really been down to my to below 1. The goal is, of course, to get it back to below are to below 1, and that also the goal for, she also mentioned earlier that we have already reached the 80,000 threshold. In fact, within a week, just this week, last week, we are the first in the ASEAN, among ASEAN countries who reached the 50,000 threshold of incidents. And so, of course, our goal is to get it back to below 5% because that's the positivity, but that's the accepted value of positivity rate by WHO. But then how can we, if we are reopening the economy gradually? Okay, this to show you that we weren't really prepared at the beginning when COVID-19 pandemic has stricken us. So our Philippine system was fragmented. There was the healthcare in the Philippines, and then pandemic only highlighted how ill-equipped the country is in dealing with disasters such as COVID-19. In terms of the emergency responses, so we had to balance public health priorities with economic and social activity, accommodating short-term measures to mitigate the spread of the virus. So what we did was to implementation of non-pharmaceutical, and this include investing in telecommunications, health innovations, and financial protection. Okay, so government so far has done centralization of response through the place to IATF or the task force. LGUs were also given the also were given the power to enact ordinances and implement quarantine and provide guidelines for some health messages, implementing quarantine, isolating areas, and distribution of cash and non-cash assistance. There was also realignment of funding, some and most importantly, social distancing measures, the congestion and restrictions on social activity and movement to reduce transmission and in turn reduce demand for health care. So there was prohibition of mass gatherings, restrictions of movement, including restrictions of air, land, sea, transportation, and public transportation, air transportation, sorry, and public transportation. And restriction of commerce, which really affected our economy. Uh, so there was limitation of business establishments and establishment operations and closure of establishments like malls, places of amusements, and hotels. So tourism was sector was very much affected. So all of these measures were called Bayanihan 1. And now because this is like the lockdown was actually the uh, being the key response to reduce transmission of of COVID-19. So I'm going to talk about the potential economic effects of lockdown, which this work actually was done way back in April 6, 2020. That was 20 days after the enhanced community quarantine was implemented. So our work has been cited already by the government agencies like Department of Finance and BSP. And so just to give you um, a brief note of what the methodology we used. So we used the Philippine Computable General Equilibrium Model, and it was calibrated to 2018 social accounting matrix with 214 sectors. And we used also Philippine Poverty Microsimulation Model to estimate the potential effects of lockdowns in Luzon and the Philippines to estimate the poverty effects. So what we did was for 1 month to 3 months, the scenarios were 1 month to 3 months, and compared it with the baseline scenario of no lockdown, which is 1 full year of no disruptions. And we used the GDP rate of GDP of 2019 as baseline. The model was also simulated by reducing the labor efficiency parameter in 1 to 0.75 depending on the coverage of lockdown. So if it is Luzon, 70% of total Philippine GDP, and if it is with an adjustment of 0.825 adjustment factor for labor, and if it's entire Philippines, 0.75 adjustment factor. So these scenarios captured lockdown factors affecting labor efficiency, such as labor conditions, and the reductions in labor efficiencies that would result in corresponding reductions in outputs. Okay, so this will just this slide shows you the possible effects of the enhanced community quarantine in the Philippines. So it's entire Philippines, and it's almost the same also as for Luzon because as I said earlier, 70% of GDP is contributed by Luzon. So this scenario is when the lockdown is for 3 months. So that was actually until June 15, 2020, and the economy contracted by 817 billion, which is approximately 16.5 billion US dollars, and relative to the 2020 projected level, and relative to the 2019 GDP, which was 356.8 billion US dollars, with a growth rate of 5.9 or 6% growth rate, the economy contracted by 2.4%. There were 8 sectors much affected for this lockdown, and the top sectors were garments, computer related, in the industry like the BPOs, and then construction, agriculture, and other manufacturers. So the government budget deficit increased to 3.5%, while prices increased by 8.8%. So the impact of the poorest group is the largest under the scenario, and the income inequality here actually decreased as well. So support also has been targeted to vulnerable labor groups in critical sectors, and it should actually quickly restore labor conditions affecting labor efficiency. The social amelioration program that gave additional support to the poor by 5,000 to 8,000 in May and June were in the right direction. So, sorry, nag-stuck yung laptop ko there. uh, in terms of the effect on the poorest household, so the poorest household groups are the most vulnerable to the COVID-19 pandemic, and combined with the lockdown, it could drive absolute poverty down. So actually, to reverse the negative effect of the 3-month lockdown, an additional 70 billion pesos, or equivalent to 1.4 billion US dollars, is required to reverse the change in all poverty indicators that you are seeing in the slides. And so the poverty effects are progressive in the sense that the poorest group, as indicated by the poverty gap of negative 2.2, has the highest poverty reduction. Noteworthy is the poverty severity that is high as negative 2.7, which captures the degree of inequality among the poor on the distribution. However, this additional budget increases the uh, deficit gap per GDP to negative 3.6%, and also increases the price by 9.2%. These effects can be mitigated with the most recent launching of the nation's largest and widest social protection program, amounting to 200 billion pesos. That's the second wave of the SAP. This amount could cover actually the most of the poor in the society, and it also includes the support to improvement of the health facilities and health service delivery in the country. Okay, so let me now go to I already mentioned about the policy recommendations there. So let me now move on to way forward. So we recommend that there should be a resumption in aggressive spending in infrastructure through build program, and continue the reforms on taxes and incentives. I would just like to show you the what we worked on before the lockdown or before the COVID-19 pandemic. We did uh, an estimate or simulation of how would the corporate tax reduction affect, and also reducing the fiscal incentives. So actually, the the corporate tax, the corporate income tax, is a major source of government income. And then we recommended that there should be a gradual reduction in corporate tax within 10 years from 30% to 20% starting 2020. And this gradual reduction would also be um, coupled with fiscal incentives reduction over the same period. So if you notice here, there's 47.7% of the total income tax revenue of the government that could be accounted for corporate income in 2018. So the assumption that the money incurred from incentives will be taken out from incentives, and this will be declared as dividend, not as additional income of the household, but should be reinvested to the system as investment, additional capital stock. With the economy that is assumed to be growing, it can be justified that there is opportunity to earn money as money flows back to the economy through investments. So if we reduce the corporate income tax, there will be government deficit, then increase inflation, increase interest rate. So the potential impact of reduction of the corporate income tax will be minimized because of the higher deficit. The challenge is how to finance the expected increase in deficit as a result of the reduced corporate income tax. Take note that the fiscal incentive given in 2017 amounted to 322 billion, and this can be used actually to uh, support the deficit. Okay. The potential effects we found out when there's gradual reduction of CIT for the next 10 years was that the macroeconomic and employment effects are and also on poverty and income distribution. The same model that we used was the CGE model and poverty and microsimulation analysis. The effect of tax reform package is actually growth promoting on employment. The poverty effects are actually shown there, and says that incidence increases during the initial years of government deficit, and it will deteriorate later. Poverty incidence declines slightly toward the later years. The decline is sustained if corporate income tax, again, is, as I mentioned earlier, fully reinvested back into the economy. However, if the increase in corporate income tax is declared as dividend income of households, the trend is in poverty reverses from later years like 2026 to 2029. I can't, oh, okay. My cursor is working. So this part here. So some policy insights from this one is that the corporate income tax is a major source of government revenue. Reduction in current rate from 30% to 20% in 10 years will result in sizable government deficit. But if the reduction can be invested back to the economy, it will be growth promoting, employment generating, and poverty reducing. And there will be potential positive effects on sectoral incentives also are reduced if the improvement in corporate income tax is not fully reinvested back into the economy. This means that if there are other sectors that don't really invest fully back to the economy, then there will be deficit as well. So now, with the COVID-19, the government has actually um, calibrated the CITIRA, that was the name of the law that was supposed to be implemented earlier before the COVID-19. And so they calibrated it to create. Create means corporate recovery and tax incentives for enterprises. So this cuts corporate income tax immediately by 5%. So not the gradual one, that's 1 point reduction every year, but this one is 5% immediately in 2020, and no change in present incentives for the next 4 to 9 years, which means income losses of about 259.54 billion pesos until 2022. So just some, sorry, I'll just skip that one. Another upcoming reform or law that's being passed is the Bayanihan Act 2. And this one is actually recover as one part 2. And it's already in its second reading. And I think this one should be supported, given that the programs that are going to be implemented here will help the economy uh, propel. Like for example, there will be enhancement of the health system and support programs for private and public workers as well, and the Department of Agriculture assistance as well. So I think I will just stop there. Actually, the Bayanihan 2 on the expenditure side will help restore incomes and jobs of consumers. And again, this will stimulate private consumption. So it is important to restore the confidence of the society to go out and spend like they used to. We need more private consumption to stir up the economy. And also, firms' operations will be subsidized by Bayanihan 2, and the recovery will probably be faster if it's going to happen. Like there will be micro and small enterprises subsidies for them, and for them to be able to comply with the health and safety protocols like physical distancing, regular disinfecting premises, and others. So I guess I would stop here, and I think I've consumed all my time. So I'll just take questions later on. Thank you very much.
Thank you very much, Dr. Tess. So we'll take the questions after all the speakers have completed their presentations. So our next speaker will talk about transdisciplinary and transsystemic interdependencies for effective pandemic prevention and management. Our speaker was formerly the ASEAN Regional Coordinator for Multi-Sectoral Pandemic Preparedness and Response. He is a consultant for emerging pandemic threats such as the Ebola, and he has been involved in whole of society pandemic preparedness and response, One Health and Continuity Operations Planning, and WHO, EDB, EUEC, and IFRC projects. He has over 35 years of work experience in the fields of microbiology, virology, transgenics, public health, infectious and zoonotic disease diagnostics, epidemiology, prevention, and control. He is engaged in various COVID-19 pandemic response efforts as member of expert peer group contributing both technical and policy recommendations. Let us welcome Mr. Noel Miranda. Noel, I think you're still on mute, so
Hello, hello.
all right, now
All
we
right,
can hear you.
sorry. Yes, good morning. And of course, my presentation is actually touching on not so much the science this time, but of course, the art. And I appreciate the presentation that actually was given before mine. And this would actually make it easier for us to understand what transdisciplinary and transsystemic interdependencies is actually focused on. So, oh, my slide is not moving, sorry.
Can you try clicking on the arrow keys
Okay,
at the
there you
bottom?
go.
Okay, there you go.
So transdisciplinary, in this case, I would like to define it as something that's integrated process that synthesizes links and extends discipline-specific approaches to generate new models for solving cross-cutting problems together, okay? So the word together here is very important. And as you can see in the illustration, how transdisciplinary is illustrated versus disciplinary and multidisciplinary and interdisciplinary. And in fact, this illustration actually came from K to 12 school, which is actually focusing on transdisciplinary learning. And I'd like to emphasize that transdisciplinary is not jack of all trades, but rather it's a person who recognizes the limits of his own trade and integrates other inputs to attain synergy. Now, being a transdisciplinarian is like an essential ingredient in a gourmet dish, where each ingredient focuses on making of the gourmet dish, and not just on being the most essential ingredient. To attain this state requires a gourmet chef who understands well his ingredients and sees the value in all. So this is a bit philosophical. And you can ask me, can we make this a reality? Well, I would probably continue with my presentation and we can all decide together. Now, one resilience unitive model, which is part of my title, actually means it's the advocacy for us to think and work as one. And all should ask, what concern of mine is also your concern? And what concern of yours is also my concern? And this is discipline and sector domain should naturally support and depend on each other. How do domains provide cross-cutting support? So that's the big question. So this is really talking about the unity of humanity in mind and action. And in this real world, we are actually, so much diseases are lurking. And these are actually driven, by disaster, climate change, land use change, wildlife trafficking, market trades, trade activities, food and water insecurity, extraction, pollution, global, and so on. And poverty here, I capitalize poverty because this is really something that's driving so many things. And you can see in this illustration as well that poverty is central, which is actually influenced by social barriers, stigma, illiteracy, lack of awareness, food insecurity, and so on and so forth. And here, my topic's actually on prevention as well as on managing the pandemic. And I'd like to talk about a bit about prevention, which is really focusing on the spillover of diseases. You've heard this over and over again, that the SARS coronavirus 2 actually spilled from animals. The bats and the pangolins are actually implicated. And for spillover to occur, you have to have these small circles or holes to actually line up together. To actually, so the probability of spillover is so small, considering the so many variables that you have to line up for spillover to occur. And this is a very good illustration of how spillover from wild animals going into domestic animals and going into the human population. Now, I'm a member of the World Veterinary Association One Health group. And so we have made these statements. One Health oversight under a common leadership is so important. That support early education is also important for One Health. And to address the social and industrial drivers of detrimental human behaviors, particularly poverty, and inequitable development and resource allocation. So here I made a problem-solving analysis showing to you the problem, the cause, as well as the effects. And particularly, I'd like to say, the separation of agencies and heads. The presentation a while ago talked about fragmentation. Now, discipline-specific approaches are issues. We kind of have silos, disciplinary silos. One silo worked on its own, so that's fragmentation. And so zoonosis prevention and control is actually divided among these disciplines: health, agriculture, environment. And so there would be slow response to emerging infectious diseases. There will be overlaps in program activities. and unpreparedness for these outbreaks. So at the end, you have poor response to emerging pandemic threats. So this slide actually is borrowed from Shaheen et al., and it's really talking about the complexity of the causal loop diagram, which is represented here, where you have environment, economic factors, social, and they all kind of interrelate and impact on one another. I can't go through this, but I'd like you to refer to this publication if you want to understand this particular diagram. So here, again, I'd like to show you the problem analysis for beyond health pandemic response, which means this is focusing on the proper management of this pandemic that we're experiencing, COVID. Of course, again, it all boils down to fragmentation within these sectors and disciplines. And you have silos among these disciplines. And then pandemic impact mitigation divided among disciplines and systems. Health, trade, economics, agriculture, etc., etc. So there will be slow response to outbreaks, haphazard response to health and non-health issues, continuing provision of essential services, for example, and unpreparedness for surges in cases, hospitalization and deaths, and social and economic impacts. So at the end of this, the effects of such fragmentation or siloed mentality would be poor response to severe pandemic impacts. That is health and beyond health. So here, back in 2016, there were actually a very important meeting where 29 countries actually gathered, and they reaffirmed the continued relevance of APSED. APSED is referring to the Asia-Pacific Strategy for Emerging Diseases under the IHR 2005. So this meeting that happened in 2016, almost 10 years, a decade after IHR and reaffirmation, where you have here Li Ailan saying that the Asia-Pacific region remains a hotspot for disease outbreaks and public health emergencies. Our shared vulnerability requires a collective effort to prepare for and respond to these threats. Okay, so that's a statement made, but really something went wrong. Okay, these core capacities that are supposed to be in place in most countries in Southeast in Asia have not and were not. So countries have not done intense preparedness and capacity building. We've shown that. So after 15 years of IHR, we've shown that we've not done this. And the Philippines in 2014 claimed that they have full compliance to APSED. Pretty much close to full compliance in 2014. But this COVID pandemic apparently has proven that this is a little bit out of the tracks. So I did actually a survey in 2012 under pandemic preparedness and response assessments under ASEAN, and also under the Prepare Pandemic Preparedness and Response Project, where we did a lot of simulation exercises in the region. And this was supported by USAID. And the Philippines high-level coordination framework were actually identified, and that included the NDRRMC and the National Security Policy on disaster, crisis, and emerging infectious diseases. Actually, the National Security Policy has a statement which reads like this: in the face of pandemics and emerging infectious diseases, the government needs to define clear protocols and procedures to ensure continuity of essential services, as well as business operations. So again, what did we do? Okay, given these structural framework or statements of policies, what have we done? Or where did we go wrong somewhere? So you can see that this actually illustrates how the structures should be cascading or transcending from a mild case of epidemic to a severe worst case scenario. And you can see the involvement of the non-health sectors becoming relevant as the pandemic actually become also more severe. And the lessons learned from the countries with all hazards framework is that most countries in ASEAN have an all hazard national interministerial coordinating body. Countries have high level coordination frameworks that can effectively activate their all hazard response systems. But apparently we made the wrong conclusions. And the key elements of multi-sectoral pandemic preparedness and response system are actually the following. We have identified this since 2013. Oversight and leadership, legislation and a clear mandate, budget and resources, comprehensive continuity of essential operations, policies and plans. Whole of community empowerment and participation, and of course, conducting regular simulation exercises to test your plans. So I also belong to a group called Pandemic Futures Initiative Groups, and we made an assessment just now for COVID-19. And this is what we concluded. COVID-19 responses are politicized, non-science driven. We require stronger whole of society coordination. As societies rush to relaunch their economies and design a more resilient future, we are overwhelmed with a plethora of approaches that are contradicting, disabling, and counterproductive. We see inefficiencies, poor interoperability, and avoidable knock-on impacts on both public health and the economy. And so this is the proposed Beyond Health pandemic risk management paradigm. Let's focus on health and socioeconomic resilience as one world community. And the mission really that we should be taking all together would be the setting up intersectoral pandemic coordination architecture within the UN system and also other regional and national frameworks. And we have to focus on harmonization of pandemic response guidance within and across sectors. So this is actually a very important model that I actually constructed sometime in 2013. And I tried to actually model this in the UP Los Baños to start a One Health education. And Professor Giselle Concepcion, who was then vice president of UP, actually enabled this meeting to happen. And we did discover that, in fact, interdisciplinary or transdisciplinary interdependencies can in fact happen, okay? Can in fact be enhanced. But we need to go through a process of understanding the problems, the disciplinary solutions versus the problem, and identifying transdisciplinary collaborative solutions. I am a little bit sad because this did not push through, and there's actually no university in the Philippines that has taken up, transdisciplinary responses to all hazards, for example, not just pandemics, but emergencies. And there's really a need for higher education to kick in and drive the process of transdisciplinary and transsystemic interdependencies. So here is a model the PREPARE project in 2009 to 2013 actually had worked on. This is the whole of society approach. We were actually the first to introduce this concept of whole of society. And the Philippines was among the beneficiaries of whole of society modeling. And unfortunately, we did realize that we need to do whole of society approach and work together, but there was just not any compelling reason until COVID came in. And this is actually a very good highlight of what the relationships may look like. We need to understand the needs of the sector. We need to understand how the sector can support government, the different private sectors particularly, how the sector cooperation mechanism can be designed or constructed, and the sector measures to maintain operations of individual actors and service providers. And all of these things put together will give you a sector linkages and interdependencies map or roadmap, and all the sectoral crisis response management structure would have been would have been defined, and communication and cooperation mechanisms would have been defined. And this is my modeling, this came out in the publication of a chapter entitled Rabies Prevention in Asia. And this is the model of transdisciplinary transsystemic interdependencies that I particularly advocate. You can see that health and well-being, together with ecological and industrial system, governance system, and social cultural system, would actually need to integrate, okay? But you need certain enabling conditions or enabling elements like integrative education, which I mentioned, research and development has to drive this. And then also integrated management and communication. But all of the actors that are part of this would be government, the NGOs, civil society organizations, industry, and the academe. I always like to say that the academe plays a very important role. And so let me individually dissect this, giving you the wicked problem at the center, which is disease outbreak and risk vulnerabilities. And you have the causal elements as well as the impacts. Now, for health and well-being, for example, looking at this, what are the scientific expertise required? Of course, you need physicians, you need veterinarians, you need nurses, medical technologists, biotechnologists, pharmacists, public health workers, epidemiologists, all of those health-centric. But you also have the non-medical contributors to this, to the health and well-being of humanity. You have local leaders, you have police, you have food and water supply services, health product technologists, social scientists, community workers, educators, engineers, the military, and environmentalists. So we have to understand that, yes, there is a health system that we need, of course, health professionals to actually try to, manage. But the proper management of the health system cannot happen without the non-medical contributors. And this is the same for ecological and industrial system. We need scientific expertise, and we need the non-ecological industrial contributors. And also for governance, we have the governance system. We also there are expertise in the governance system, such as national local leaders, legislators, educators, communication specialists, logisticians, strategic planners, various technical experts, the military, police, social scientists, community organizers. But there are, again, contributors, which we have to include the medical professionals, the social workers, the engineers, industrialists, and environmentalists. And of course, this is for social-cultural system. Again, you have the direct contributors and, the scientific expertise, the direct contributors to the system of social-cultural system, as well as the non-direct or indirect. For the direct, of course, I'd like to emphasize that the economists are very important, anthropologists, human ecologists, communication specialists, urban planners, business managers, housing experts, gender experts, and of course, sociologists and community workers. And I have just 2 more slides, if you will allow me. So what are the considerations for Beyond Health? Beyond Health is actually equal to working together. So the question to us is, have we really achieved this end where we are actually working together? If this problem-solving model is not explicitly defined technically or philosophically, we cannot harness well-coordinated participation in action. We need to elaborate beyond health operationalization. The structures, framework, and leadership are important. And there is no clear beyond health operational model. At this time, we might not be able to get anywhere if we don't work on this model. So how does working together look like? Have we clearly defined the art and science behind this working together model? So to me, one resilience, or whatever you want to call it, is we need a unitive model or a unitive problem-solving model for attaining optimal health, whether that's going to be something that will prevent the spillover of pathogens like COVID-19, or that will allow us to manage the worst case scenarios of this COVID-19 pandemic. So finally, my recommendations, and these are, I believe, are success factors. We need integrative leadership, of course. We cannot integrate without leadership. We need a mandate for this leadership, the policies and coordination plans and strategies. What makes one think integrative and be a good leader? We need higher education to create good leaders. We need people like, people on this Zoom call, on Zoom meeting. We need to drive this process of creating leaders. So remember that everything is governed by karma. Our actions or inactions today determine the good and the bad outcomes of tomorrow. COVID-19, of course, the determinants of success should have been set yesterday and not today. We failed to do certain things yesterday, and the outcome is what it is today. What can we still do today to save us from this COVID-19 disaster? Well, as the saying goes, we are, in fact, building the plane as best we can while we are also flying it. But the key here is really to build the plane as best we can, scientifically, methodically, unselfishly, in non-political ways, in more responsible ways, and for the common good. Transdisciplinary and trans-systemic interdependencies for effective pandemic prevention and management requires all of us to work together. Let's all collaborate to construct this working together problem-solving operational model. And this is really my call to everyone, not only in this call, but to the Philippines, to the world, to UN, to everybody involved in this fight against COVID-19. So thank you very much for.
Thank you very much, Noel. So again, we will be taking questions after our two more speakers. Okay, the next talk is about the leading evidence-based actions through data science, or LEADS, for health security and resilience consortium, breaking scientific silos, collaborating across sectors, engaging political forces against COVID-19. Our next speaker is a public health official with business, health management, and economic evaluation qualifications. He has more than 7 years of progressive work experience in the areas of tuberculosis and health system strengthening, health economics and financing, health technology assessment, management and innovation, and implementation science, both in the Philippines and and abroad. Currently, he is a chief executive officer and co-founder of both the Innovations for Community Health, an NGO implementing sustainable and scalable market and private sector oriented health system innovations and social enterprise for TB, and the Meta Health Insights and Innovation, the first HTA focused firm responsive to the needs of the 2019 Universal Healthcare Law. On the side, he is also doing consultancies for local and international agencies, of which leading the Philippine team of a 5-country evaluation of tuberculosis digital adherence technologies and working on TB innovative financing are current highlight engagements. In the Philippines, he is a multi-awarded student and youth leader, of which being one of the 10 outstanding students of the Philippines in 2014 and the 2019 Australia Alumni Excellence Young Achiever Awardee are considered as his foremost accolades. To respond to the COVID-19 pandemic, he convened LEADS for Health Security and Resilience, which is a consortium of public health and data science professionals. In Australia, he served as the chairperson of the statewide Filipino Student Council of New South Wales and the founder of the nationwide Filipino-Australian Association of Student Councils for Empowerment Towards National Development. That is all. Welcome our next speaker, Dr. Jason Alacapa. So Jason, you may now share your screen and unmute.
Yes, Kathleen. Give me a moment because I'm logged on with my iPad and my
Okay.
I'm supposed to share it using my laptop, but I'm having difficulty. So give me a moment. I'm transferring the file to my iPad so that I
All
can
right,
share it.
sure. No worries.
Unless you can give me an access, the other one without the picture.
Okay,
To
hold on.
share,
Ah, okay, okay, okay. Hold on.
yeah, I don't have a share screen access
All
to
right,
that.
all right. I can. All right.
Please, thank you.
Okay, there you go. So you should be able to share using your laptop now.
All right, give me a moment. Okay, so can everyone see my screen?
Not yet, Jason.
Yes.
Oh, you can.
All
Yes.
right.
Okay, now yes, yes. All right. There we
All
go.
right, thank you. So, good morning, good afternoon, good evening, wherever you are. Thank you for this opportunity to share our experience with Leads for Health. So, unlike the many others who started this great annual symposium, who discussed a lot of their scientific findings, this presentation is more of to share our experiences and some lessons learned with this consortium. So I would like to take off from what Dr. Miranda was beautifully elaborated earlier about transdisciplinary and multidisciplinary collaboration. And this is one example on how it was exemplified during this COVID-19 pandemic. So to start off, this presentation is entitled Leads for Health, that's L4H for short. It's breaking scientific silos, collaborating across sectors, and engaging political forces against COVID-19. So LEADS is short for Leading Evidence-Based Actions through Data Science for Health Security and Resilience Consortium. So I'm the co-convener together with Dr. Mike Salazar. And as I would always say, I'm just an instrument with the great work that this great team is currently doing. So quickly, this is my presentation snapshot. I'll be going from the problem, a little about the consortium, the specific solutions that we have deployed, lessons learned, and conclusions. Problem. As we know, COVID-19 pandemic posed a threat with magnitude and complexity beyond what Philippines or any country has experienced. And it's but timely now that our cases is breaking into 100K now, considering the gap of of the diagnosis validation. So as we know, national governments are overwhelmed and local government units or LGUs are often left for themselves to act. This is markedly pronounced during the first few months of the pandemic that the government it was scrambling on what to do, and the local government units went on their own selves to implement their own solutions. So one major challenge that our team was able to identify is how to empower these decision makers, local decision makers, to respond quickly and effectively and efficiently based on the available evidence, all in the background of competing priorities to implement actions on the ground and save lives right away. As such, there should be a focus on what we call as the government frontliners. And these are the LGU and their stakeholders. So in such situations, when the national government is overwhelmed, LGUs could receive less national support. Thus, helping them could be potentially life-saving millions, or thousands, or even millions of Filipinos. So hence, this is our response, the L4H Consortium. This is the story goes back in March 2020. It was a meeting by the Analytics Association of the Philippines, wherein prominent data science people spoke. We have Dr. Jomar Rabahante. I think they have Dr. Darwin Bandoy. He's also here, I think. And we have Dr. Michael Promentilla. And some members of the PSPHP, the Philippine Society of Public Health Physicians, relatively a newly formed professional society for the non-clinical doctors like us. I think Dr. Raymond Sarmiento is here as well. He's also a member. We initiated this conversation. And then we tapped them beginning with the initial meeting. And this consortium grew to include numerous institutions and individuals, mostly in the areas of public health and data science. Quickly, these are the institutions involved, from the Professional Society of Public Health Physicians to academe. You can find De La Salle University, the University of the Philippines, Ateneo School of Medicine and Public Health. There are some initiatives within the university, like the UPLB Biomathematics Initiative, of which Dr. Jomar Bahante is heavily involved. There are some consulting firms, Meta Health, of which I'm a co-founder together with Robert Leong, who presented earlier. We have Serolytics through Dominic Ligot and the Analytics Association of the Philippines. So as you can see, this consortium exemplifies a mix of institutions coming from different backgrounds, from the academe, from the private sector, and from the non-governmental side. Quickly, these are the initial founding members. I won't go through these names, but basically what I would like to highlight on this slide is that we are approaching the issue using a multidisciplinary lens. And recently we have Dr. Ador of De La Salle University from the Political Science Department who joined our team as well. So he's providing a different, additional synergistic perspective on how we tackle things related to COVID-19. So officially, who are we? So we are a consortium of professionals from the academe, civil society, and the private sector coming together in the wake of the evolving COVID-19 pandemic. So we do capitalize our diverse but synergistic disciplines. So it's basically in the intersection of public health and data science. Vision, a responsive and resilient Philippine health systems against global health emergencies. So please do note that although we were formed during the wake of COVID-19, we are looking beyond COVID-19. We're specifically focusing on aspects of health security and health resilience. Health security referring to responding to global health emergencies, such as this pandemic, and health resilience focusing on more a holistic approach to response, recovery planning, and more of preventing similar issues and disasters in the health sector. Mission, how do we achieve this vision? Basically through data science analytics against COVID-19. The value proposition or the value that we would like to add to our stakeholders is this: catalyzing data-driven action, transforming public health security and resilience nationwide. So we're coming from a data-driven approach, converting them into actionable insights. Hopefully, this will transform public health security and resilience. Specific solutions. So quickly, we, just like the many others, we also initially deployed some dashboards, and it's currently hosted through the PSPHP website, but soon enough, this will be migrating to its own platform with more features. So we're now currently on our second version of release, and we do have quickly two sets of solutions. One is dealing with time-varying epidemic indicators, of which RT is included. And we do have a co-informed heat risk map. I'll be discussing this quickly in detail after this. So to begin with, the time-varying epidemic indicators, this team is led by Dr. Peter Julian Caton of the UP Diliman School of Statistics. And we have Robert Neil Young, who presented earlier from the University of New South Wales. So quickly, the time series data this shows the time series data on the developments of COVID-19 in the Philippines. Our team is one of the first who tried to show an RT reproductive number in the Philippines. Much of the focus was initially with case fatality rate, the absolute incidence rate ratio of COVID-19. But as early as March, April, we deployed our own RT calculation, initially scraping off the data from the Johns Hopkins website. But currently, what we do is we try to triangulate it and verify it with a daily COVID-19 data drop. So while we do have an automated process through an R code, however, there are a lot of data challenges related to the daily DOH data drop. So that's why it still needs a daily handholding and screening. And I believe with the tenacity of this team through Dr. Peter Caton, because he's able to churn out these analyses on a daily basis. Aside from that, we also feature a real-time confirmed case fatality rate. So unlike the usual CFR, this one is delay adjusted considering the delays in reporting. In the earlier days of the pandemic, sometime April and May, the delay was noted to be around 16 days. And now it has been markedly reduced to less than 5 days, owing to our, I would say, improving data systems through COVID Kaya. It's like a centralized platform for collecting primary and secondary data for COVID-19. Here's a snapshot of that slide of that product, the time-varying epidemic indicators. I believe previous speakers were able to show time-varying R. So just to recap, the goal is to reduce this value to less than 1 because this indicates the level of community transmission of COVID-19. So as we can see, it has grown up after opening our doors from the lockdown. But now we are steadily declining, albeit we are having thousands of cases on a daily basis. So this dashboard can give real-time insights to our decision makers. The second solution, the co-informed risk heat maps. This one is co-led by Dr. Promentilla. I think he's here as well, of the De La Salle University, and Dr. Jomar Bahante of UPLB and UP Open University. So basically, this is an adaptation of the European Commission's INFORMS framework. INFORM is a it's a resilience framework in which we tried to adapt with COVID-19, hence the name co-inform. Co stands for COVID-19. It's a composite heat map with several variables included in it. I'll be going through it later. So what's the value of such dashboard to our stakeholders? Basically, these risk index comparisons and visualization may potentially accelerate not only national but also district level actions to developing pandemic. Aside from that, since the focus is on health resilience, it does not only dealing with the current pandemic, but will also aid our stakeholders in drafting preparedness plans to mitigate future impacts. And lastly, it could help nudge multi-sectoral actions. Later on in the following slides, you will see that the variables that feed into this heat map are actually coming from various disciplines. And if you involve these various sectors as well responsible for these various indicators, it could possibly nudge multiple or multi-sectoral action. There are three main dimensions feeding into the co-inform model. So these three are the following: hazard and exposure, vulnerability, and resilience gap. So hazard and exposure, this is where variables related to COVID-19 incidents, modeling of incidents comes in. Vulnerability, there are various factors related to the vulnerability of a specific locality, city, municipality, or province. And then the resilience gap. So this one is the model, the co-inform model or COVID-19 index for risk management model. So these are the three variables which I have mentioned earlier: hazard and exposure, vulnerability, resilience gap. So below it, you will see a lot of different indicators feeding into these main dimensions. At the indicator level, for example, for hazard and exposure, this is where the proportion of the infected in the population goes in, the outbreak threshold, the number of probable suspected confirmed cases. For vulnerability, indicators feeding into this specific dimension include the following: poverty incidence, number of potential fatalities, unemployment rate, etc. And lastly, for the resilience gap dimension, some of the indicators that feed into this are the following: LGU health expenditure, workforce demand, critical care bed demand deficit, PPEs, LGU response effectiveness. So this is the ideal model that our team is currently working on. We would like to, there's a disclaimer though, that not every indicators are now feeding into our co-inform model. The hope is in the future, as we localize with LGUs through our future projects, we would be able to include more indicators and assess the effectiveness, the internal and the external validity of this model. Also, as of this time, we put equal weightings to all three dimensions, so 1/3 for each of the three. The goal is to calibrate this further hopefully through future studies. This is a snapshot of our co-informed risk heat maps. So this one shows the aggregation on a national level, but at the provincial one. So it's a color-coded heat map from green to red, considering from low to the high values depending on the risk index that you're trying to view. This one shows the composite COVID-19 risk index, meaning all three dimensions feeding. And as you can see, there are some red areas, some orange areas, and CR would be orange, Cebu would be orange as well. So you could disaggregate the view depending on the region, province. We don't have a city and municipal level yet because the granularity of data needed would be challenging as of this moment. And then we can also disaggregate the variables to be viewed. So for example, this slide shows us this specific variable. So I have highlighted here the outbreak threshold, or the DOH active case over our outbreak threshold for the NCR region. As you can see that almost all our cities in Metro Manila are in the highest rating. So these are some of the variables where you could also disaggregate our maps. So you could look into the different dimensions, different indicators that we use to feed to this model. Some lessons learned and potential indications, implications to the academic, scientific, and engineering community. Disclaimer though, these are my personal reflections and not of the group. So I've categorized them into five key areas, thematic areas. First, breaking silos. So as you've seen, although we've only involved public health, data science, and now social scientists in the team, we've been championing this mantra of breaking silos, breaking the academic silos, institutional silos. It goes beyond academic colleges or institutions. It went beyond universities, university silos to collaborate and produce meaningful outputs and hopefully impact. We also adhere to open data and open science. That's why our methodology is quite open. If you look into our website, there's a tab for technical notes. You will see details on how we came up with these models and these dashboards. There's also a reflection on increasing focus on translation and implementation sciences. And as we say, everything that we do in science, as we publish, the goal is really to translate this on the grassroots. And aside from this, in public health, there's a field called implementation science. It just focuses on generating the evidence to deploy interventions and to deploy pilot and to transition them to full scale up. And both of these disciplines, emerging disciplines, actually harness the multidisciplinary approach. So these disciplines are not confined in a specific silo, but they straddle across disciplines. After all, solutions, innovations happen if we are collaborating. Another reflection under breaking silos, this is just more of a personal one. Could there be a shift in measuring academic performance matrix? I know there are a lot of academics in this Zoom meeting, and I have always wondered because most of the universities by default and even university ranking websites would measure first and foremost the performance of a university based on the number of publications. How about changing the metrics to increasing the share of the impact of the research to the society? If we do have a metrics on how we measure these things, and these universities actually encourage or assess the academics on how they translate these into impacts, perhaps silos would be broken down and collaborations would be promoted. I have alluded a lot to the second lesson, collaborating across sectors. There's definitely synergy across sectors. And I think one of the least explored or untapped resource is the private sector. They have resources at hand, but usually they don't know what to do. So as academics, as scientists, as experts coming from the other sectors, we can tap the untapped potential of private sector. As far as L4H is concerned, we've been pitching to the different conglomerates during the start of the epidemic to show our solutions, hopefully adapt this to their solution, to their needs. Another sub-realization or reflection under collaborating across sector is securing additional sources beyond the traditional means. And by traditional means, I mean here research funding. There are a lot of developmental funding that we can explore, especially in a crisis situation like the pandemic. For the experience of L4H, we initially pitched our dashboards back in March and April through the USAID Office of Health. And now we're happy to announce that in the coming months, we will be deploying our platform to at least 7 local government units from Luzon to BARM through a USAID funding. So what started such a passion project for the members of this consortium, and then we started pitching it to stakeholders and potential funders, actually came into fruition into something that we could really translate on the ground. Next lesson is focusing on the gap. there are a lot of dashboards produced during this pandemic season. And what our team has been focusing since day one is not to duplicate what's already existing on the ground. Hence, we tried to produce the RT dashboard, which now feeds into the UP's and COVID dashboard website as well. And we focus on developing this co-inform model through the lead of Dr. Promentelia. We also need to learn how to do environment and market scanning. This is still related with opportunity scanning. We could focus on the underserved or unserved need so that our solution would have a faster, would be taken up by the stakeholders on a faster scale. And then we're really targeting on an area where nobody else is working. And the focus is also always on what value can you add compared to the existing solutions. Next is engaging political forces. I just put one word there. It's inevitable. I think as experts, as scientists, as academics, we should not veer away. We should not be allergic from engaging political forces because at the end of the day, I believe everything is political. And this issue, the COVID-19 pandemic, it is ultimately political. So we need to use our expertise, the evidence that we have generated to engage these political forces so that our outputs would translate to meaningful impacts at the grassroots level. And lastly, going beyond. Although we are a consortium focused on COVID-19, we look beyond that. So we're looking into health security and resilience as overall frameworks. We would like to advocate for a multidisciplinary CDC-like institution, whether a separate or built in within the existing institutions we have right now. This is where the One Health approach would come in, specifically discussed by the previous speaker. And we would like to continuously engage, even beyond COVID-19, to do technical assistance and research on these matters. And we are opening our doors, so we are open for memberships as well. If you think you have some good ideas and you have value added to the floor, definitely our team is very much open to welcome you to the team. Conclusion. So let's move our science from bench to bedside, as we say in medicine, and even beyond. So how do we do this specifically? We can do this by first breaking our scientific silos within institutions, across institutions, collaborating across sectors, and engaging political forces. As of July 27, 2020, the COVID-19 fight is far from over. Hopefully, through our collaboration, whether through L4H or elsewhere, we would win this fight as soon as possible. With that, thank you very much for listening, and I turn over the table to Dr. Aviso. Thank you.
Thank you very much, Jason. So we'll take the questions again at the end of this session. So for our final speaker, he will talk about the risky business of biorisk assessment and COVID-19 pandemic, local perspectives. Our speaker is recognized for his important contributions in the field of microbiology. He had an undergraduate degree in medical technology from Silliman University and a master's and PhD in microbiology from the University of the Philippines, Los Baños, with subspecialization in molecular genetics from the Universidad de León, Spain. He received a citation for excellence in doctoral research from the Area de Microbiologia, Universidad de León, and the Department of Science and Technology PICA-starred outstanding dissertation in advanced science and technology for the characterizing the regulatory function of the Homo aconitase gene in Penicillium chrysogenum. He is currently working on the characterization of virulence genes in Serratia marcescens, and he finished a training course in biotechnology and crop protection sponsored by UPLB and the International Rice Research Institute, and attended several biosecurity training workshops sponsored by the Sandia National Laboratories of the U.S. Department of Energy and the U.S. State Department, as well as the Joint Defense Threat Reduction Agency of the U.S. Department of Defense, UPNIH Philippine Advanced Biorisk Officers Training Program. Let us all welcome our next speaker, Dr. Franco Teves. Okay. Franco, maybe you can turn on your
Yes.
video. Yes, okay.
Okay, so before the presentation, I would like to greet everyone. Good morning and just to inform you that my presentation is pre-recorded. That is to minimize any possible glitch due to instability in connectivity. Another thing is I would like to limit my talk to only 15 minutes and to simplify my presentation. So thank you. I hope you would be able to get the meat of the presentation this morning.
What I wish to share is how one university office can significantly help the surrounding community in times of a public health crisis, such as the current COVID-19 pandemic. Perhaps not all universities have set up a biosafety or biorisk office. This short presentation will hopefully encourage all institutions to have one. To begin, let me recall with you a little bit of recent history of the COVID-19 pandemic, which is important to a biorisk officer based on published reports. I was tracking and monitoring the spread, but never really realized that it would become a pandemic in about 2.5 months since Wuhan. It reached the Philippines on January 30, 2020, and the first case in Mindanao was reported from my city on March 8, 2020. Thereafter, outbreaks were reported in several places in the Philippines. The objectives of this presentation are the following. One, to describe the role of the University Biorisk Office in times of public health crisis. As most eyes are upon medical doctors, nurses, and medical technologists in the fight against COVID-19, not known to many are biorisk officers in the background evaluating the risk posed by the novel coronavirus. Second, to demonstrate the applicability of laboratory biorisk management principles to field biorisk assessment. One who is grounded in laboratory biorisk management will not find it difficult to work in the field, as in evaluating the risk of a pandemic. And third is to demonstrate the critical function of the University Biorisk Office in influencing policy, which for me is a game-changing role of a biorisk officer. Any institution with an existing biorisk office and trained biorisk officers have an advantage. Thanks to the National Training Center for Biosafety and Biosecurity, which handles the Philippines Advanced Biorisk Officers Training, or the PABOT program, with the U.S. Department of Defense, Defense Threat Reduction Agency, or DTRA, the Department of State, the Sandia National Labs, the UP NIH, the National Committee on Biosafety of the Philippines, the UNEP Biosafety Clearinghouse, and the American Biological Safety Association, which have provided invaluable inputs. MSU IIT Biorisk Office had a lot of preparations since January 2020. And until now, a lot of preparations, a lot of activities are ongoing. We need to learn a lot of things about the novel coronavirus. And so we had to look into published reports from the website of the WHO, the CDC, and published articles, especially those in the New England Journal of Medicine. We also did a lot of review and study on international biosafety, biosecurity, and biocontainment principles. And we conducted several fora on COVID-19 because at the early stages, there was already a tendency for the public to panic. And so we figured out that there has to be a way to give correct information regarding the COVID-19 problem. Now, laboratory biorisk management principles are very, very important in our particular case now, and we just have to tweak some of the principles so that we can make use of this for field biorisk assessment, in this particular case for COVID-19. Biorisk management consists of three basic steps. One is biorisk assessment. This is followed by biorisk mitigation, and then the last is performance, when we do all the mitigation plans and make this a reality. A review of the basic concepts is also very important. For example, what is a biohazard? It is any biological agent that possesses the potential to cause harm on humans, animals, and plants. Biorisk consists of two important components: the likelihood of infection and the consequence or severity of infection or exposure. And so we have the so-called risk equation, as can be seen in the slide. Now, laboratory biosafety consists of containment principles, technologies, and practices implemented to prevent unintentional exposure to pathogens and toxins or their unintentional release. This is from WHO. For example, it is believed in the US, for example, that the COVID-19 is a biological agent that has escaped the from the Wuhan Institute of Virology. If that is the case, there is unintentional release, and this is an example of a breach in biosafety protocols. Laboratory biosecurity, on the other hand, refers to the protection, control, and accountability for valuable biological materials within laboratories in order to prevent their unauthorized access, loss, theft, misuse, diversion, or intentional release, again from the WHO. The key words here are unauthorized access or intentional release. Then we have field biosecurity, which is quite different from lab biosecurity in the sense that the organisms we deal with may or may not be well characterized. Our work area may not have well-defined perimeters, and our work procedures are very flexible to conform to very different and rapidly changing situation. Biocontainment refers to confinement of materials that are harmful or potentially harmful to life. So these harmful or potentially harmful materials consist of bacteria, fungi, viruses, toxins, and tissues. These are also called biological hazards or biohazards. Okay. As they remain hazards unless someone is going to handle these biological materials, and in the process of handling, there is now a risk that is involved. There are two important goals why we did a biorisk assessment, why we conducted this, not only for our university, but for the entire city. One is to inform management of the level of risk of viral transmission in the university and in the community. Second is to help the management decide on appropriate mitigating measures to reduce the risk. This is important because as a biorisk officer, he does not have the authority to make the decision, but he or she can help the management make the decision through a very good risk assessment. So the methods that are used are standard methods in biosecurity risk assessment. We begin with hazard identification, and in this particular stage, we no longer have a problem because we know that the hazard we are dealing with is the novel coronavirus. First, it was referred to as a 2019 novel coronavirus, then referred to again as the SARS-CoV-2 virus, and then more recently with the COVID-19 virus. Then once we identify the hazard, what comes next is hazard characterization. And this really takes a lot of work because we have to read a lot of materials regarding the virus. For example, what are its characteristics, its route of entry, its infectious dose, its incubation period, and all the other characteristics of the virus. Once we have enough of this information, we move on to the next process, which is on risk characterization. And this particular stage, we now ask the questions, what is the likelihood of exposure to the virus? And what is the consequence of exposure? And then the result of this is what we call as our risk evaluation, when we have the risk level estimated. This is then given as a report, and of course, with a accompanying list of mitigation measures. If management considers the level of risk as acceptable, then there's no other action needed. But if the management thinks that the risk level is gray, mean is high and needs to be reduced, and therefore we have to be prepared to also propose some mitigation measures. In doing risk assessment, there are several methods. We can have a qualitative risk assessment. We can have also a semi-quantitative risk assessment. And then we have the quantitative risk assessment. So for a rapid risk assessment, we can make use of the semi-quantitative risk assessment protocol. And in doing so, we make use of a risk matrix, as can be seen on the slide. On the x-axis and the y-axis, okay, so on the y-axis, you have the likelihood of occurrence of a particular adverse effect or event. And this ranges from, the descriptors used here are 1, rare, unlikely, possible, likely, or almost certain. And these are given numerical values from 1 to 5. The descriptors used for consequences are insignificant, minor, moderate, major, and catastrophic, also given numerical values from 1 to 5. And so if we now have a combination of the likelihood and the consequence, we would come up with a particular estimate of the risk from low risk to medium and high. We selected 10 risk parameters, such as social distancing, the wearing of face mask, and then also including control of mobility across the city borders. And we did our risk characterization and then our risk evaluation. And if you can see here, in all aspects, in all of these risk parameters that we have chosen, we have a high risk level. And so we made use also of proposal for mitigation measures. We submitted this, the complete report was submitted to the LGU. Okay, so for example, how we compute for the risk. A question that could be asked is, what is the risk of contracting COVID-19 in Iligan City with no social distancing, knowing that many COVID positives are asymptomatic? So we make use of the risk equation, okay, which is equal to the likelihood, and we can multiply this with the consequence. So for the likelihood, it would be likely to people to be exposed to the virus if social distancing is not practiced, and the consequence is estimated to be a major consequence, and therefore if we multiply the two, we now have 4 times 4 equals 16, and if we take a look again at the risk matrix, the risk level is high, so as can be seen here. Now, the other important function of a biorisk office and a biorisk officer is on the aspect of policy. So it's very important. I would call this a game-changing role of the biorisk officer because a policy is very important. It points direction of a course of action. And in doing so, for example, in our particular case, we, because of our risk assessment, we incorporated this into our proposal. Okay, proposed exit protocol upon expiration of the enhanced community quarantine or ECQ in Iligan on April 30, 2020, and the possible transition to general community quarantine or GCQ, impinging on MSU IIT and other local institutions. So roughly about 70 to 80% of our proposals were incorporated into the policy, the guidelines from the city government. So in conclusion, a university biorisk office is vital in times of public health crisis, such as the current COVID-19 pandemic. And the principles from laboratory biorisk management can be applied for field biorisk assessment. And that risk assessment results can be used to influence policy aimed at reducing the level of risk through appropriate mitigating measures. Thank you very much.
Thank you very much for that presentation. Okay, now we'll move on to the questions for our speakers. May I request all speakers in the second half of our session to please turn on your videos so that everyone here can actually see you. Okay. All right. All right. Our first question is for Dr. Chonko. So this actually came from Franco. So how long do you believe the government can sustain its programs to mitigate the economic impact of COVID-19? It is very probable that COVID-19 pandemic will extend up to the end of 2021.
How long I thank you for the question. How long it's really uncertain, but as long as we have strong, we have the stimulus package, fiscal policies, and then we maintain the financial systems, we maintain and manage the financial system to be stable, then I think we're okay. As what Secretary Dominguez said, keep on saying that we started with a strong macroprudential. So I think we can still borrow money, but then the government has to earn. So there has to be some collection of tax collection. So we'll be able to survive, I think. Until next year, yes, we can. We will. Thank you. With
Okay,
the of the economy.
Thank you, Dr. Tess. Our next question comes from Hilman Mendoza. So, is there any limitation on the use of CGE in modeling economic impacts when the economy is somewhat dysfunctional, restricted functioning with lots of externalities, for example, in a state of disequilibrium? The second question is on the macroeconomic level, what do you think? What do you think of the current economic? Sorry, kind of lost it. Current economic Bayanihan collective. Oh, sorry. Yeah, okay. What do you think of the current? Where am I? Economic response of the Philippines to the pandemic. Do you think the country has strong fundamentals to withstand the economic shock to the economic system? Specifically, do you think the country now has good fiscal policies or sound financial system in place to enable the country to recover economically post-pandemic, perhaps more efficiently and sooner rather than later? The Bayanihan or collective action was also highlighted by former NEDA Secretary Pernia. Public spending and private consumption are the key. So, any questions? Any comment on that?
Yeah, thank you again for those questions. For the CGE, well, the reason why it's called computable general equilibrium model because it solves the problem, like whatever the shocks that you put into it, it will always make it will always come out with a solution that is in equilibrium. So the markets will always clear. So if there's some externalities, those are external shocks that you can include in the model. So the end will always be aggregate supply equals aggregate demand with the prices and so on. So it depends on the assumptions that you put in. But yes, you can solve that. But those the externalities will be exogenous shocks to the model. So on the fiscal policy, like the Bayanihan Act 2, yeah, I actually support that, except the one on the calibrated corporate income tax, because the acronym create will definitely put the economy down, given that the decrease in corporate income tax is so outright, like it's this year 5%, and there's going to be already a big deficit if we do that. But I understand that the government really wants to stir up the economy, especially encourage foreign direct investments. That's why they're cutting the corporate income tax by that much outright. But they have to think of the consequences, because we're gonna be in deficit for a longer time. And of course, Secretary Dominguez again mentioned that we can borrow, given we started with strong macroprudentials, we can borrow up to 50% of our GDP, but we don't want that to happen, right? And with the Build program, I have strong support on that. The government should really push for it. Although Build, BBB has another B, which is borrowing, and that's what we're doing. But the multiplier effect is high, so like employment creation, and then support to businesses. So I guess with that we can recover. And I already mentioned about the monetary policy earlier on. So with the macroprudential policy, that framework that was just released by the central bank, I think that would really manage the systematic risk that the COVID-19 is really creating now. So it will increase resiliency in the financial system. Thank you.
Thank you very much, Dr. Chonko. The next question is for Dr. Miranda, also from Hill. So, to me, the true transdisciplinary implies blurring of disciplinary lines, meaning willingness of each discipline to step out of their traditional methods and, in fact, cross fertilize their approaches or methods. Not a group of experts working together but still using their own traditional tools. It seems to me that the problem analysis flowchart should still interdisciplinary. High level coordination and being holistic are necessary, but not sufficient for an approach to be transdisciplinary. The question is, how do you plan to operationalize step three? Knowing how deeply experts hold on to and believe the value and power capability of their traditional tools. The causal map or mental map is a good start, but a unified transdisciplinary tool to analyze is still lacking or elusive.
Okay. First, I'd like to thank Hill for asking this question, which is very important. And I, in fact, agree with you, Hill. Transdisciplinary model, or even going beyond transdisciplinary, which is trans-systemic, is actually at this moment conceptual. And in fact, this is something that's the reason why I agree with you. We have to blur the line, or in fact, I would put it in another term, it's a kind of a recombination, a recombinant thinking, where we are actually working together without necessarily doing things in parallel, but actually doing things together. As not as me as an economist, or not me as a veterinarian or a medical doctor, but us together as responders to a wicked problem such as COVID-19. And that's why I agree with you. And so what I perceive to be happening is that for us to get to the transdisciplinary thinking, or transsystemic thinking, is that we have to first perfect interdisciplinary collaboration. We have to perfect that because we're starting from in fragmentation. We're starting from siloed thinking and siloed approaches. So to get through to the point of transdisciplinary working together, we need to go through a process. And education and leadership is important, as I had explained. I'm not now the section 3. I'm not so sure what that is, um, um, but pretty much what I would like to say is that it is conceptual and operationalization, as you said. In fact, a case study, for example, do we have a case study in the Philippines that it can actually represent transdisciplinary collaboration? Thank you.
Thank you very much for that, Dr. Miranda. I think what Dr. Jason presented is an initial step. Well, if it's not yet the complete transdisciplinary step, I think it is a good step towards achieving that particular purpose. Perhaps Dr. Jason can comment on how the team is working about having different experts within their group.
I think it started from a genuine need and passion to help out. But I think a lot of it has to do with the culture of the individual members and collectively of the institution. Because to begin with, these experts are coming together with an open mindset that it's important to collaborate. I think that's very important, as in many institutions, if you're looking into an organizational development perspective, culture is always the first step. If you don't have it, no matter what systems we place around it, we won't be able to achieve our goal moving forward.
There is a follow-up question for you. How can we further improve our infrastructure for a better data science or health security and resilience?
Yeah, I think this from Dr. Lau. Thank you for that question. I think there is no fast and easy way forward to improve the infrastructure, the data related infrastructure of the public health system. However, what is important now is what's happening with the COVID-19 pandemic. It's actually a policy window. So if I'm going to quote Kingdon's theory, so we do have the problem on data in the pandemic. We do have the policies, supposed policies to solve these issues. And we have the political will now because we have more money, we have more interest, more salience for this issue. So we need to strike this golden opportunity to create advocacies. And this could be top down and bottom up. Top down, we could have advocates for policy lobbying, maybe a law related to including improving the data infrastructure of the public health system, and bottom up, such as the L4H consortium, the academe coming together to advocate for these things. So it's really advocacy, and it will start with policy. And the opportunity, golden opportunity is now. Thank you.
Okay, thank you. The next question goes to Dr. Teves. It is also from Hill. Do you think our regulatory infrastructure or legal framework, including laws and enforcement procedures, is already in place to regulate biorisk situations or occurrences? If not, do you think it is necessary to have one? For example, has there been significant case to warrant such a legal initiative? Is there any initiative, bill, or municipal ordinance to cover this particular risk?
Okay, thank you very much for the question. The answer is in the affirmative. For example, I have here with me a copy of the Presidential Executive Order number 112. I think this is the mother legal framework for the community quarantine. And of course, the Constitution of the Philippines, for example, Section 15, Article 2 has been also mentioned. And then there is this proclamation number 929, series of 2020, declaring a state of calamity beginning in Luzon. And the Bayanihan to Heal as one act. And then with this mother framework, legal framework, government agencies, line agencies also, followed suit. They also, released guidelines, like, for example, to govern the work schedule of or adjustments for government workers. We have the Civil Service Commission issuing their memorandum circular number 10, series of 2020. And then you have the Department of Education, you have the Commission on Higher Education, and then the Department of Public Work and Highways also, issued memoranda or memorandum circulars. So in terms of laws, I think we have enough, but the problem is in the implementation. We can see, or I don't know, in Manila or in other places, but we do have a problem here in Iligan. Okay, it has been reported that Philippines is the second highest, in terms of compliance to the use of face masks. Second, according to a research, a survey. But I don't know if that's going to be true to all parts of the Philippines. And we still have that problem, the enforcement aspect. And worse, if the enforcers themselves are the ones who are breaking the law, okay? Not wearing a face mask, not adhering to social distancing and all of this. So we have these problems. We are very good in promulgating laws, but I think we have our weaknesses in the implementation. So even in the municipal or city level, we have, because for example, in our case in Iligan, the Office of the Mayor issued the Executive Order number 40 series of 2020, declaring the entire city of Iligan under modified community quarantine and providing for its guidelines. This is after the ECQ. So based on our risk assessments, we were able to assist the local government unit in coming up with an appropriate set of guidelines. So guidelines and laws, no problem. The main problem is in the enforcement. So I hope that we will improve somehow in enforcing this already existing laws. So that's my answer.
Thank you. The next question comes from Dr. Angeline Lau. The way we are disposing biohazardous waste from COVID-19, how do you think it affects us? Does personal use and improper disposal of masks increase our risks?
Yes, again, the answer is in the affirmative. That's the reason why I believe that hospitals, for example, should have a trained biorisk officer. So I don't know how many hospitals have trained biorisk officers, because the disposal of biological waste, especially biohazardous waste, is really, is critical. The storage of the waste itself, where is it going to be stored? What are the conditions during storage? Are there rodents and pests that are present in the storage location? So these are important things. And then another thing is the proper disposal. Okay, we have to inform the general public on how to dispose. For example, when we get rid of our old face masks, we don't want our face masks to be just scattered anywhere. We can look into either chemical or physical means of neutralizing the virus, for example. Currently, it is being considered, and I think there's much discussion in Manila right now on the requesting for modification of our law regarding incineration of waste. I think this is currently being discussed and debated on in Manila, okay, because we have a very strict law regarding incineration. However, we are already incinerating dead bodies. Those COVID-19 patients who died, okay, we cremate their bodies. And in a sense, it's really incineration. But for other materials like other biohazards, we should have a clear law regarding this. So I hope in the coming days we will have concrete proposal from a group. I think there is a group in Manila discussing this now to be presented to the national government. So you are right. There is really a need to take care of our biological wastes.
Yeah. Perhaps Dr. Alacapa can comment on it, being a physician and more involved, I guess, I suppose, in the hospitals. You generate more hazardous wastes.
Yes, I agree with Dr. Tevis' pronouncement that we don't have any biorisk officers are not required for hospitals, except if they do have higher laboratories requiring higher biosafety level 2 and above. But at the minimum, they do have the pollution control officers or PCO, which is not only unique to hospitals, but also to other institutions or businesses generating hazardous waste.
Okay, so thank you for that. So I would just like to get the consent of our speakers that maybe if our participants would want to get in touch with you, will it be okay for them to send me an email and then I'll connect them to you guys afterwards? Okay,
Yeah, sure.
so thank you very much. So that closes this particular session. But before we end, let me just share my screen to invite you to other sessions of our PAASE. Okay, let me share. Excuse me. Sorry. Okay, so like I mentioned, this is the second week of our 40th PAASE anniversary. So lectures and sessions and talks are still ongoing all the way to August 14th. There are scheduled presentations from Monday to Friday from 8 o'clock in the morning. So if you want to see the complete program, so just kindly scan this QR code. It will take you to the website of the Philippine American Academy of Science and Engineering, and you can find there a link towards identifying the program. Next is for those of you who want to get to know more about our activities, you can find us on Facebook. We also have our website, which is paase.org, and we conduct regular webinars on Fridays from 8 to 10 in the morning, except that we're on hold right now because we're celebrating our anniversary. But all of our webinars, including this one, will be uploaded in our YouTube channel, Paase Webinars. Okay, so with that, I'd like to close the session. So thank you, everyone. And if you have any questions for our speakers, please feel free to send me an email um, so that I can get them in touch with you. Okay, thank you, guys. That's all.
Thank you.